Yeah, so hello and welcome everyone. So let us start this session. Today we are going to focus on propagation, wave propagation in dielectric media. Yesterday we talked about specifically for air propagation, and in the bottom half you can actually add a silicon domain or a silica glass or multiple layers in the bottom, and you can have an air dielectric interaction. Today we are going to talk about on wave propagation through of a particular mode. It could be a fundamental mode or a higher order mode, and how it can actually propagate through a dielectric media such as optical waveguide. It could be a rib waveguide. It could be a optical fiber, slot waveguide. So all this type of waveguides it can propagate. So what I'm going to share is the basic approach to do that, and once you know the basic approach, you can actually use the same approach to model any complicated structures. Okay, I will share my screen. I hope you can see my screen now. Can you see my screen now?
Yes.
Okay, cool.
Yes,
So,
sir, visible.
okay, cool. So basically, if you see any optical fiber, for example, or optical fiber or any dielectric waveguide, if I draw for the optical fiber, it will look something like this. Okay, something like this, right? So there are two kind of cross sections that you can actually take to simulate or model in COMSOL. One of the approach is to take a or it's kind of a two kind of cuts I can do. uh, okay, so someone is trying to join the meeting, let me add them. Okay, yeah. So there could be a two kinds of cuts that I can do. I can do a horizontal cut or I can do a vertical cut. Okay. If I do a horizontal cut, this is what it would look like. Okay. If I do a horizontal cut, it will look like something like this. Okay. Which is also known as longitudinal section. Okay. And another approach is to do a vertical cut, which is also known as transverse cut. Okay, so if you do a transverse cut, you will see something like this. I hope you are able to understand, right? So what is horizontal cut and vertical cut? Any questions or doubt in this case? Okay, so in most of the cases that we model it with in optical fibers, it would be either this case. Okay, it would be either the longitudinal sectioning or it would be a transverse cut. Okay, it is highly means improbable that people would be modeling these 3D structures like this. Okay, it's kind of very minimal. People use a 3D structure to model in COMSOL or any other software because of the meshing requirement. People usually will work like this as a horizontal cut or longitudinal cut, or the vertical or the transverse cut. Okay, any questions, anyone?
Yeah. I have a question. My name is Faraz, and
Mm-hmm.
as you mentioned that mostly we are going to use horizontal cut and vertical cut, and it's in rare cases we use 3D in
Hmm.
COMSOL,
Yeah.
3D modeling in COMSOL. So, as a as a as a as a as an engineer, as a simulation engineer, since I'm basically from PCB designing background, hardware designing background. So as an engineer, how can I detect that For this case, we have to go with the horizontal cut. For this case, we have to go with the vertical cut, or we cannot go with both of them. We have to go with the 3D modeling. So how we can decide?
Yeah, that's an excellent question. The first thing is that, as you said, you are working with PCB, right?
Yeah.
So in those cases, you are working with megahertz or gigahertz range. Okay, so
Yes.
that
Yes.
is not a problem. You can still go for uh, 3D modeling. If you see, many PCB models are available in COMSOL. You can
Yes.
still, means
Yes.
it will be still computationally expensive, but it's not going to be that challenging. The
Yeah.
issue with optical is that we are working with ranges of like terahertz, like hundreds of terahertz, like 200
Yes.
terahertz, 300 terahertz frequency, which actually results into nanometer scale of wavelength. In the case of PCB, the wavelengths are in order of meters or order
Yeah.
of the value. So that answers a part of your question. Next question is like, uh, if you assuming that you are working in optics, and
Yeah.
you have to make a choice whether you go for a longitudinal or a transverse cut, so which one to use for. Now that depends upon what is your requirement. Okay, for example, you want to do some mode analysis. Okay, so mode analysis, if you want to do, for example, finding the fundamental mode, which is the fundamental mode of your
Yeah.
optical fiber. Okay,
Hmm.
you want to know the higher order modes. Okay, so these are the reason why people go for uh, this transverse cut. Okay, perform the mode analysis. While if you want to actually know how uh, uh, electromagnetic wave or mode actually, not even the mode, means it not be the exact mode, but how does electromagnetic wave propagates through media. Okay, so then
Yeah.
you actually go for a transverse cut. Okay, you want to know how the Evanson fields um, around the core cladding interface. Okay, then you actually go for longitudinal or horizontal cut, right? So here you can actually see how the wave actually propagates. Okay, that is the main change. So here you can see how the wave propagates inside this, and you can
Okay.
also see how the wave actually um, dies down. Okay, so actually we'll see that electrical field will die down. So these are the Evanson's fields you can see based upon the interface. If you have some kind of plasmonic structures or metallic structures with negative value of permittivity, so you can actually see the some kind of plasmonic effects on this, because of which it actually can work as a filter, for example. Okay, uh, next, in the case of vertical cut, horizontal cut, that is the transverse cut, you can actually see the modes. So the modes you have: LP11 mode, LP01, 1, 2, 2 modes. There are a lot of other kind of modes that may exist in this optical fiber core. Okay, so all these modes actually you can figure out using the mode analysis. Okay, if there are multiple modes, you want to know the mode overlaps. Okay, so even those mode overlaps you can actually uh, see within this mode analysis. Okay, you can find what is the modes, fundamental mode and higher order modes, and what are the overlaps between the multiple modes.
Thank you.
Okay, so that is kind of the reasoning why people go for either this and this one. But as you see, both are not the actual picture of what we are modeling. Okay, so if you see this 2D structure and this 2D structure, it is important to know that in this case, this is a cross-sectional view, that is transverse cross-section view of this one. So even though our optical fiber is finite, for example, uh, 10 centimeter or 1 centimeter or 5 centimeter, but what COMSOL will assume over here is that the optical fiber
Yeah.
is infinite length. Okay,
Yeah.
that is the assumption that it is going to take. In this case, it will not even consider it as a circular. Okay, So we just assume this as a rectangular block of fiber which is kind of extending to something. If you draw in 3D, it will look something like this. Okay, like this, which is kind of propagating over here. Okay, so this block, this slab of uh, of core, which is kind of extended to again infinity. Okay, this also is extended to infinity. This, all the sides are extended to infinity. Oh, sorry, not this side. Here we are pumping, and here we are seeing the out, but this other sides would be actually extended to infinity, out of plane and inside the plane. Okay, does that helps?
Yes.
Okay, looks good. So, so these are the two basic operations, ways of approaching an optical fiber media. Okay, so let us see and understand how should we proceed. Okay, so let us start with the first hands-on this structure, that is a longitudinal cross section. So quick raise of hands of how many people would be doing the models with me, so it will help me to understand. Okay, that looks good. So many people are doing. uh, okay, so so this is the first thing. You need to select what is the space dimensions. So let us select the 2D, because as you see, it's a 2D structure that we're going to model. Okay, so let us select a 2D, and then we go for optics and wave optics, and we choose electromagnetic waves frequency domain, EWFD. Okay, okay, first we need to select 2D, and then we need to select we go to optics, wave optics, and electromagnetic waves frequency domain. Okay, so I hope you are able to add this. Now we need to go to the study. Okay, so here it's where the things will start to change now. Okay, we need to actually perform mode analysis, but let us not add it as of now. Let us add only frequency domain. We will add the boundary mode analysis at a later stage. Okay, you need to do more boundary mode analysis to figure out which mode uh, we need to excite. Okay, but let us not add it right now. You can add it later as well. Let us choose frequency domain model and click on done. Please select frequency domain study and click on done. Okay, so I hope you are able to create this this with me. Okay, now let us create a structure which is similar to this one. Okay, so let us create a slab, dielectric slab, which is having a length of around how much 5 micrometer, and uh, thickness of around 1 and 7 micrometers. Okay, so let me just right click on geometry and add a rectangle. But before that, I have forgot that you need to change this length unit from meter to micrometers, because we are going to work with micrometer range. So please change it. This is one of the best practice approach. So please don't miss on changing these length units. If you work with meters, your life would be very difficult at a later stage. So please change this length unit to micrometers. So it's just inside the geometry one and go into the micrometers. Okay. I hope
Excuse
you
me,
have.
sir.
Sorry. Yeah.
Sir, I just missed out the point which how you defined the parameters. There was a network issue, I guess. Here.
I have not yet added any parameters as of now.
Okay.
Hmm. Yeah. So I have not added any parameters. I've just completed the model wizard and here I am. Okay, just I've changed the geometry length unit from meters to micrometers and nothing else I've done. The next thing what I am doing is to create a geometry of a slab kind of a structure. So right click on geometry and add a rectangle. Okay, width, you can see that now it is in micrometers, so your life is simpler. Okay, you don't need to add like 10 power minus 6 and all those things. So your width could be 1 micrometer and height would be, okay, slab width could be around 5 micrometers and height could be 1 micrometers. Okay, this much. Okay, and you can make it in the center by pulling it downwards, that is around minus zero point 0.5. Okay, so here you can see that the central line is matching with the zero. Okay, the zero is going to the center of your slab. So this is not kind of compulsory, but again it's kind of best practice method. So always try to keep your origin at the center of your geometry. Okay.
But the x axis is not on zero. Is on, I think, two, between 2 and 2.5.
Sorry, can you come again?
Yeah, you are saying that we have to put this box, as you mentioned, that on
Okay,
center.
well, you mean this one? No, that
Yeah,
should be
yeah.
fine. Yeah,
Okay,
yeah, means that's fine. Only this fine is because your propagation is in this direction. So
okay,
ideally,
okay,
in this way, it's fine. This
okay,
one is
okay,
also
okay,
fine. Yeah.
okay, okay, okay. Thank you for clarifying.
Yeah. Okay, looks good. So I hope you are able to create this rectangle of this structure. Okay, you can next do duplicate this rectangle. Okay, and make this height as 7. And if you draw it and pull it, if you draw it and build this, you will see that it's actually goes above. So you need to pull it downwards. To pull it downwards, again you have to make it half of that height. So you make it 3.5 and you can see something like this. Okay, then click on zoom extents and you can get something like this. Okay.
Uttam, it's pulling from the edge of the rectangle or from the center.
Yeah,
So you see,
edge, the corner edge, the
edge.
left bottom edge of this. So now if you see this
Okay.
left bottom edge is 3.5.
Yeah, yeah,
Okay,
yeah, yeah, yeah,
the
yeah.
same thing
Okay,
I'm
okay.
pulling. Hmm.
Thanks.
Yeah.
So,
Yeah.
hello.
Hmm.
Yeah, for me it is going beyond the screen.
Yeah. So just click on this zoom extents.
Okay.
It will bring your geometry back into your
Uh,
GUI.
yeah, got it, sir.
Hmm.
Thank you.
So how many people are along with me after
Excuse me,
making the
sir.
geometry? Yeah.
Can you show the rectangle one again?
Okay.
Okay, thank you.
Hmm. Both are the same width. Height is 1 micrometer, other is 7 micrometers. I'm pulling first one down by zero point 0.5 micrometers and second by 3.5 micrometers, so that my central is matched with the zero. That's not compulsory, but that's what I say. It's kind of best practice method. So I think people are with me. I think so. Okay, looks good. Okay. Any issues? Just let me know if anyone is facing any issues while making this model. Okay, so the next part is uh, uh, can anyone guess what would be the next part?
Material selection.
Yeah, material section could be the next part. So if you right click on the materials, you can either add from library or you can add your blank material. Let us today add a blank material. The way to add a blank material, even yesterday I think Padma Priya was asking about water, right? So she was kind of quite surprised that the material was like air, and then we changed the material properties, it became water, right? So if you don't want to be so surprised, then you can add a blank material and then apply whatever material property that you want to give. Okay, for example, I add a blank material, right? So uh, I can give what is the material property of this one. For example, I give it as 1 and 0. Okay, so it actually works as air domain. Oh, sorry. So for 3 words. Okay, that's good. So now all the three domains are working as air domain, whether irrespective of what I write over here. Okay, this is what happened. Sorry. So in just write over here air or clad. Okay, what I'm saying is this cladding is made up of air. Okay, let us start with the simple, and you will see that we'll make it more complicated later on stages. So okay, any questions even facing? Okay, let us now give the material properties for the core. So right click on the materials, blank material, and then write core, and I select this central domain and give the refractive index of 1.5. Okay, we'll wait for a few seconds for you guys to add this.
Please repeat once again.
Which step?
The one which just mentioned, the defining the properties of code.
Yeah. So I
After,
just yeah, right click on materials and blank material. So I just rename it, the label as clad. Now by default this would be selected to all the domains, right? So now you can see that it's overridden by the second domain has been overridden by the core over here, right? So here I'm given it
okay.
1.5 real part, and cladding I'm giving it as 1 refractive index. Okay. Another important part is that the imaginary part is 0, which means that it is a lossless domain. Okay, that's very important part. As you will see in some time that it can be also lossy, but actually in real world, no material is lossless, right? It's a perfect lossless material, which is kind of very difficult to actually
Uh,
get in practice. Sorry.
Pratham, I have a small question. My name is Faraz.
Hmm.
That in clad material one. So when I go there, I just I there here there are three boxes. So only one box is selected. How to select rest of two boxes in clad one?
So clad is outer two domains.
Yeah. So how to select the second? Yeah.
Yeah.
The
No, second is now overridden by my second material
yeah.
here.
But my screen shows something else. Could I share my screen with you?
Yeah, yeah.
Okay. I'll share immediately so we can proceed. Can you see my screen?
Yeah, I think it's loading.
No.
Yeah, I can see now. Okay, so by left clicking, are you unable to select? Just left click the bottom two domains as well. Yeah. So
Yeah.
yeah, it's coming right. So now it's fine. So you don't need to add two means. I
Okay.
will show it by. I want to show that by default all the domains have been assigned material by default. So but now you
Okay.
go to
And
core. That's fine. That's good. Now go to core and select the second. This is fine. You're
it's
good to
fine.
go.
Okay. Thank you.
Mhm. Yeah, looks good. So anyone facing any challenges? Do you want me to repeat any steps? Okay, I hope. Uh,
Um,
Could you repeat
sir,
core.
the test?
excuse me, sir.
Yeah, there are two
The
people
core
thinking.
step,
Sorry, which step? Core.
defining core.
Yeah. So I just add another blank material. Select the central domain and apply refractive index as 1.5. So like this, right click on materials, blank material, select the central domain. Then automatic this material properties will pop up. Here I write 1.5. That's it. And then change the material as core over here. Okay. Yeah. You have one more questions, I think.
And we can do vice versa as well. Like we can change the name
Yeah, yeah,
of the
yeah.
material and then put the refractive index, and we can do that.
Correct, correct, correct. Yeah. Name is only a label. So
Yeah.
even if I write water over here, it doesn't make it water. Or if I make any other, so label is just a name.
Yeah.
Main thing is this one.
Man, thank you. Thank
Okay.
you. Thank you.
Mm-hmm.
So I have a doubt.
Mm-hmm.
So in first material, for
Mm-hmm.
clad, we are having all three surfaces.
Domains. Yeah. Mm-hmm.
Okay, domains.
Because in
So
2D we'll
in
call it
core,
domains. Yeah, I mean I understand it's a little bit different. So when we are in 2D
uh,
structures, so we call surfaces as domains. If you are in 3D structures, then
okay,
we call 3D volumes as domain. It goes. That's how it
okay,
definitions have. Here boundaries means edges. Yeah.
okay,
Yeah. What's the question?
okay. Yeah, but in core, we are having that central
Mm-hmm.
domain
Mm-hmm.
and we are having the refractive index 1.5.
Mm-hmm. Yes.
Yeah, that's it. I wanted to confirm that.
Okay. Okay. Looks good. Any other question by anyone else? Looks good. Okay, so now let us go for electromagnetic waves. You can see here which equation it is running is Maxwell's equation, wave equation. I don't want you to
Sir,
change anything. Yeah, yeah. Sorry.
I'm sorry. I actually put that in my question in the chat. So, what
Mhm.
does the overridden mean actually, and which priority it takes when simulating?
Overridden
And I
means
guess,
yeah, geometry.
or is it?
uh,
I don't know.
no. One way why people like I try to use overridden is because sometimes what happen, Sujay, is that you might have a very complicated geometry at a later on stage. Okay, there
Uh,
will be not just three domains, there will be 70, 80 domains. Okay,
okay.
so sometimes what happen if you have a habit of not adding all the domains as a very docile material like air, then you
Mm-hmm.
might sometimes forget to apply the material to that domain, especially you're looking like hundreds of domains, right? Maybe not 100, maybe at least tens of domains, like 70, 80 domains you might have. And sometimes you might miss the material assignment to any of the domain, right? So if you have a
Okay.
best practice method to apply air, like a very simple novice material, like it will not kind of hamper a lot of to your simulation. So it will
Mm-hmm.
always good to apply this to all the material, all the domains, and then keep on assigning what is what. So in that
Okay.
case, what will happen? No domains would be left unassigned as a
Okay.
material. Mm. And then
But
once you
yeah.
click the study results, you will get some solution. Then you can figure out that this result is little bit issue at this domain. Perhaps this must material assignment might be an issue. Then you can figure out coming back to your from the results you can see. Otherwise, it will keep on saying that material means it will give you computational error means now
Okay.
couldn't able to solve. It could also say that this material has not been assigned the
Also,
this
domain
domain
is
has been not
unassigned or something. Yeah.
material. But yeah, as a best practice method, we keep on assigning
But
The
the last priority, so the last time you assign it to a domain, that is the priority it takes, right?
yeah, correct. You can see over here that overridden by clad
Correct.
material one.
But
Yeah, so
if you change the position now, if you remove the
yeah, it would be
two,
opposite. So last one would be the correct one. That is
okay,
correct. So if I
perfect.
make it opposite,
Understood.
I will make it like top, then this one would be given
Correct.
the
So then
priority.
it will
Yes,
take it
now you can see.
as a air rather than core.
Yeah, so now all these
Understood.
three are clad now.
Okay, got it.
Right.
Thanks.
Yeah, correct. The last one, bottom one has the highest priority, correct. And that is true for all of the complete tree. So this is a kind of tree geometry. So in this tree, the last one always has the highest priority if you are looking for even boundary conditions. So if I apply PEC to these three boundaries and then I again apply PMC to these three boundaries, same boundaries, then it will take whatever is in the end. That is the PMC. Okay. So
Okay,
bottommost
understood.
node has the highest priority. That's how COMSOL works. Yeah.
Thanks.
Okay, looks good. So now we go to the wave equation. This is just for your understanding that we are using a refractive index. Okay, so it's very important that we know what material model we are using. You might be interested in dispersive time kind of material like Selmayr or Debye or Root Lawrence, especially for modeling of metallic materials. So I can show you in the end about plasmonic filter, waveguide based on plasmonic filters. Okay, so that's it. Next, anyone, any guess what is remaining? What should we do next? Any guess?
Port.
Okay, good, very good. So is it, what's your name? Sorry.
Jay Krishnan.
Oh, yeah, Jai Krishnan, yeah. So the next thing is the ports. So right click on this electromagnetic waves and assign the ports. Now, assignment of ports is very interesting in this case because this is a cross section of my optical fiber. Okay, that is very interesting. So, uh, so I don't know, for example, which kind of mode may exist in this particular optical fiber. So it would be ideally be a kind of a Gaussian kind of a mode that may exist, something like this. Okay, so if I draw over here, maybe I use a different color of pen. So it's, oh no, not like this. I'm doing which kind of cross section? I'm doing this cross section, right? So it looks something like this. Okay, this kind of mode may exist through this wave, and it's how it actually propagates through this structure. Okay, so the way that I need to use is the numeric type of port, right? So numeric type of port is COMSOL will figure out its modes, fundamental mode as well as higher order mode based on the material property of all the three domains. Okay, for example, if you had the refractive index very high over here and low over here and here, then the electromagnetic wave would be launched from the top. Okay, but in our case right now, the core has the higher refractive index, right? So the the Gaussian wave mode would be actually propagating. This fundamental mode would be more prominent in the central domain. Okay, so let us use type of port as numeric. Let COMSOL do the work to find out the mode. You don't need to worry about it. Especially with optical fibers, any waveguides, you always use numeric kind of ports.
Excuse me, sir.
Mhm.
Sir, what is the difference between periodic and numeric port?
Numeric port is specifically for, this is not repeating structures. Okay, so in
Okay, okay,
if it is a repeating structure, then you can, for example, there's again range of core again in over here in the top, right? So at that time we can use the periodic port, right? But in this case, this structure is going to just, so if I draw this and I pull it down to my notes, okay, if I draw over here, so if you see, what we will eventually get is something like a mode which will be something like this. Okay, the same thing will actually propagate here forward. That's what we want to see. Okay.
yes, sir.
Mhm.
Yeah, thank you, sir.
Yeah, so this is not repeating structure, so the core is not repeating in the on the top and the bottom side. Okay, there's no repetition, so that's why we use numeric ports.
Sir, I have one
Okay,
more
Is
understood.
it
question.
So,
mean,
Uh, uh,
sorry, Jansi.
sir, actually, yes, sir, numeric means is it like we are adding number of points at one particular boundary?
No, it's just a way of saying that. I don't know why the name is numeric. It maybe looks confusing, but what does it do? What does it do is that it tries to find out the modes that may exist. Okay, so it could be fundamental mode or higher order mode. Any type of mode it will try to search for, and then we can launch that particular mode. I will show you how to launch that particular mode once you figure out the mode.
Oh, okay, sir. Yeah.
Hmm.
Yes.
Yeah, sorry, there's one more question.
yeah, Sujay here. So
Mhm.
is it possible? So if in a real life situation, we generally try to align our source to the core region, and
Correct.
we try not to. So generally, like, okay, if we want to see how it propagates in clad, we do align it differently, but generally we align it to the core region, and then we vary a little bit to get the best results out of it. Is it
Mhm.
possible? So right now, so why we do provide this ports, so input ports to the clad region? That is the first question, and second, is it possible in COMSOL to do this minute alignment study where we misplace or we change the placement of the source and see how the propagation happens?
Okay. Yeah, the first question I will try to respond. So here, why we give numeric port not only to this central domain but also to be the cladding domains. Okay. So now, if I'm assigning this to domains, you will see that I am talking about this region as well. So these kind of events and waves. So that events and fields you can only figure out once you apply the numeric port to the surrounding boundaries as well. Okay, so based upon the refractive index of the core and cladding, it will actually show you if there are any events and fields which are kind of nearby, which are dying down in the region. So that is the reason why numeric port requires all the boundaries to be selected.
But in
Okay.
real life, so even if we apply so let's say we discuss about the real life problem, when we apply the source only to the core, then evanescent field actually generates. So it is actually the
Yeah, yeah,
remaining
correct,
power
correct.
that goes
Yeah.
to the clad region. So
Yeah, yeah, yeah.
necessarily, if you are only adding the power to the core, the field automatically will leave through the core region and to go to clad
Ah,
region. So you don't need
correct.
to like, in theory. So
Okay.
how I understand.
Yeah, yeah,
You
I
get the point, right?
understand what you're saying. Yeah, yeah, I understand. So what you're saying. So based on the numerical aperture, you're trying to only
Yeah.
excite the core. Yeah.
Even if you
Uh,
excite core, depending on refractive index difference, you will have
yeah, yeah, it
either
will
evanescent field
give
or
these
you
fields.
won't have.
Yeah.
So you
Yes, yes,
don't
yes.
particularly when we do this not sorry, experiments or study, mathematics, a theoretical study also, we only apply
Mm-hmm.
the field to the core and then
The core. I
automatically
see.
the
Correct. That
field
is
goes
true.
towards
Yeah, yeah,
that.
yeah, yeah. That over here also you will see that to happen.
Yeah.
Um, but why do
So
we
this is like
only up?
counterintuitive. I
Uh,
don't understand the reason. Like,
uh,
yeah, it is not intuitive to give the 1 and 5 to the as port one.
okay.
But yeah, if it is
Mhm.
the process, I don't know. Maybe we can try not giving 1 and 5 and see
Yeah,
the
yeah, we
which
can
case
try
it is
at
like.
yeah. Once we complete this model, we can explore
Sure.
the other varieties, and you will see that it should be working. It should not be like it's not working. So here we assume that the light source is given
Sure.
to the complete domain instead
Correct.
of only
So it
the
is like
central
a
domain.
huge
Yeah.
source going through the
Correct, correct. Yeah.
complete side
Correct,
of
correct,
the
correct. Yeah.
structure. And the
Correct, correct.
second one, do you like have you seen this
Mismatch.
COMSOL? Yeah,
Uh,
can we try this? Like,
Mismatch. Yeah, yeah. Sorry, you're saying something. Sorry.
yeah,
Mhm.
can we try aligning, so changing the position in like some micrometer here and some micrometer there and see how it. So, for example, if you only want to excite fundamental mode and then you find the best position, then you misplace the source and how you see that not only fundamental mode gets excited but also some other modes are excited, and that's what you can say that those are leading to more losses and so on and so forth. So some
Yeah,
sort of
that's
that
very
kind of
interesting
study.
actually. I never
Okay.
thought about those. Neither we had any like yeah. Mm, but I'm just thinking, how do you make it possible? Nothing is coming on top of my head. Perhaps we'll think about this. I
Okay.
will think
Sure.
and get back to you in this one-on-one session. Perhaps
Sure, sir.
I will have to think. Mismatch. How do we create here? There would be approaches to do it. Uh, I'm not getting in top of my head. Yeah, let me just
I
think
have
a little
seen
bit more.
one model in ray optics.
Mhm.
So it should work with fibers because
Yeah,
fiber geometry is rather
yeah, yeah.
bigger.
Ray
And you
optics
can
is kind
actually,
of very simple way to mismatch, so that you can
and
easily
yeah,
do that.
but
But
in
here,
this it would be more, yeah. So
little
I'm
bit
just
more.
like curious because we have
Yeah.
some sort of those kind of devices where we want to do that study
Mhm.
and compare it with the experimental part.
Yeah.
But yeah, we can then discuss it later. Thanks.
Yeah.
We
Yeah.
can
No. No.
continue right now. Yeah.
Oh, yeah, yeah.
Thanks.
You
Thanks.
can definitely do it, but I have to think about. So it's not would be not. It will not be a trivial way. It will be something like non-trivial. I have to think
Okay.
about it. Yeah. Looks good.
Sure.
But excellent question, Sujay. Yeah. Thanks. So next thing is I apply port to my all these three boundaries, and my next job is to apply. But this is the source port, so I need to also apply a listener port because it need to also absorb my energy that I am releasing from here, launching from here. So one way to do that would be just duplicate, okay, and then I remove all the boundaries, and then I select all the listener boundary over here. Just make sure that the wave excitation is off over here. Okay, so here you apply port. Here you see the color of it's kind of more bright red, means it is kind of acting as a excitation port, and here is like dull red, which is kind of absorbing the domain. This is colors is red over here. So okay, so the only change from port 2 is the boundaries is changing, and the type of excitation is changed to off now.
Sir,
Hmm.
for me, the arrow is still uh, towards each domain. It
Yeah,
is
here you make it off. Wave excitation is off.
yeah. Thank you, sir.
Hmm. Okay, so here you will see that all the boundaries have been given some boundary. For example, here also by default PEC has applied to all the boundaries. Okay, but you can see that some of them are overridden. Okay, so internal boundaries like this one is not applicable. Okay, other overridden. So on the top and the bottom boundary has been given as PEC, and that makes okay sense because most of my fields are going to die down in this domain. It will not go so much far over here which to reflect. If you want, you can also apply PML in the top and the bottom, but right now it's not that not significant losses that is going to happen. Okay. Okay, so the next thing is to just see the mesh. Again, mesh is important over here very much because this we have to follow lambda by 5 by the refractive index. So you can see that the mesh is more refined in the center because of the refractive index 1.5. It's kind of more relaxed in the cladding because refractive index of 1. For example, now if I make the refractive index of 3, for example, okay, then I see the mesh, you can see that it will be more refined even further. Okay, so higher the refractive index will make your life more difficult, especially for propagation. Okay, so right now I have 1.5 refractive index and 1 over here, and now comes to the crucial part of how we are going to launch the wave. Now frequency domain is used for frequency domain is used for this domain. Okay, this domain. So once you have the mode, you can actually launch it uh, within this domain, internal domain. Okay, so frequency domain is used for this, but to find out this mode, okay, to find out this mode, we have to do the boundary mode analysis. Okay, boundary mode analysis is very much similar to the mode analysis that you do over here. Why it is called boundary mode analysis is because we are doing in a kind of a domain structure. Okay, so we are applying mode analysis on a boundary. That's why it's known as boundary mode analysis. Okay, but it's very much similar to the mode analysis that we discussed some time back to find out which kind of mode we want to launch with. To apply boundary mode analysis, you just need to right click on the study one. You need to go to the study steps, click on other, and click on boundary mode analysis. I will wait for a few seconds to add so that you can add this boundary mode analysis. Okay, just right click on the study one, go to study steps, go to other, and click on boundary mode analysis. Okay, so I need to apply boundary mode analysis to my both the boundaries. So I need to apply um, over here as well as over here. Okay, all these complete boundaries I need to apply. Both the places I need to apply. Okay, so over here it is port 1, that is P1. Here it is P2. Okay, port 2. So right now it is for port name is 1. Here you can see this port name is 1. Frequency is what we have still not defined. So let us go first and define the wavelength. From that, frequency we can define. So let us go to parameters and define the wavelength, which I forgot. I write 1550 nanometers, and I write f naught, which is my frequency, as c constant divided by LDA naught. Okay, I'll wait for a few seconds for you guys to add these two things, wavelength as well as frequency. So how many you guys are with me? Just quick raise of hands. It's good. So LDA naught is 1550 nanometers, and F naught is C constant by LDA naught. Okay, so now I can go to boundary mode analysis, and over here in mode analysis frequency, I write F naught. That is nothing but C by lambda. Okay, and one more important part is search for modes around. So this has to be the core refractive index, because you don't want to search around your cladding. You want to search for the modes around the core. So you need to write over here 1.5. Okay, there are a lot of variations that you can do over here, but I don't to talk about it as of now, because I'm just building up the simple model. But later on I can actually, if you have questions, I can talk about the other parts. So otherwise you keep it as default as of now. Okay, once you have added this frequency f naught, and sorry, yeah, you have a question, anyone?
So this is Dharma. Can you open one of the parameters?
Parameters, here I've applied these two. I can also share in this Google chat. Yeah, I have shared it over here as well. Okay, it's LDA naught, and always use the units as square brackets, nanometers.
Yes, sir. Thank you.
Okay, looks good.
Excuse me, sir. Chetan
Yeah.
here. Sir, I have
Mhm.
a doubt. I am using COMSOL version 6, in which the mode search method in your software shows around shift, the method selected. Whereas in mine, I have an option of manual, region, or all. So, what should I be going for, this all or region?
By default, what was there?
By default, manuals.
So keep it manual.
Okay.
Yeah.
And also, sir, how do you exactly, maybe after the simulation is over, can we once discuss fundamental mode and boundary mode? Because I want to just understand when do I have to go for boundary mode analysis and when do I have to go for fundamental mode analysis? Under what conditions do I decide which one to go for?
No, no.
Is it
So fundamental mode, or you want mode analysis? You're saying?
yes, sir, mode analysis and boundary mode analysis. Sorry.
Yeah.
That-
So here so that depends on the cross section. Again, if you are doing this cross section as longitudinal cross section, then you need to apply boundary mode analysis on the edges of this.
Mhm.
If you are using numeric ports, that's what you will be
Okay.
using, right? For
Okay.
this, if you're doing a transverse cut, then you go for mode analysis. Both are the same. Both of them are same only, but it depends
Okay.
upon you are actually applying to the boundary. That's why
Okay.
it is known as boundary mode analysis. Here you are applying to the domain, perhaps the
Okay.
cross section of that. So you apply known as mode analysis. But both of them are physically internally the same. It's find out the modes, all the
Okay, sir.
modes.
So it is more of a problem centric and geometry centric that we are
Correct,
doing.
correct. Yeah, yeah.
Okay.
Application.
Sir,
Thank you.
if I will apply the frequency domain analysis in this rectangular section, will the result will differ?
Sorry, Kavita. Can you come again?
Sir, in the rectangular section which we are using currently 2D structure, for
Uh-huh.
the mode analysis, if I want to go for the mode analysis, either instead of
Uh-huh.
frequency domain, if I directly use the mode analysis study,
Yeah. So
will it affect?
yeah, it will definitely affect. So what it will mean is that the cross section of the optical fiber is like this. Okay.
Hmm.
So then you're taking a transverse cross section, and then you are doing a mode analysis on this one. So it will try to figure out modes which are existing over here. Understand? So that is different. What we are doing here is the longitudinal cross section. So like this one over here. You
And
understand,
sir,
right?
in the case of optical fiber, we have the leaky mode or HE11, HE21 mode, LP01, LP11 mode. Is it possible to analyze all these modes in this console study we are doing?
Yeah, yeah, definitely. There are many people have done this. So if you see, we will do it in some time about this. When we do the transverse cut mode analysis, I will show you all the modes that you can study.
We will able to see the HE mode and LP01, 02,
Yeah, yeah, yeah,
21.
yeah, yeah, yeah. You should be able to see all the modes.
Okay, sir. Okay, thank you,
So
sir.
actually, it all those hybrid modes. So you'll see the fundamental mode and overlap. So there are two modes that become a hybrid mode to give you T11 mode, TM mode,
Yes. So
right?
weekly
So yeah,
approximation is there. That's
yeah,
because we have that hybrid mode there,
correct, correct.
and
Yeah, but you should be able to see all the modes. I can
and so
show
the
you.
electric field plot we want to plot if the field strength at the core and the cladding electric field strength.
Yeah,
Can we
you can. I will.
plot that
Yeah,
or
yeah, we can plot it. Yeah, definitely. I will show you.
okay, sir.
Okay, that's good.
Yes, sir.
Yeah, that's good. Okay, so we are in boundary mode analysis for the first port. So now it is the time for the second port. So just right click on this step 2 boundary mode analysis and just duplicate it and apply it for the second port. That's it. No need to change anything else. I just duplicated my first boundary mode analysis and I just changed my port name to 2 instead of 1. Okay. And next, as you understand from this geometry that I have drawn over here, the first thing is to find out the modes. Okay, the first thing is to find out the modes at my entrance as well as the at the exit. Okay, and then comes the propagation. Okay, the first thing is to find out the modes at the entrance and exit. So the boundary mode analysis needs to be done first, and once we know the modes, we can then launch that mode using frequency domain. And that is why this frequency domain should be in the end, and first and second should be the boundary mode analysis. Does that make sense?
Sorry, sir. Can you say again?
So the
Try again.
frequency will also change in the frequency domain analysis as
Yeah,
F
yeah,
naught.
correct, correct. Yeah, yeah, correct. So here it should come F naught. Yeah. Sorry, there's one more question.
The frequency domain needs to be at the end.
Yes, yes, yes. Because we are going to launch that particular mode using frequency domain analysis. But the first thing is to find out the modes at the entrance and exit of our modeling regime. So that's why we first find out the modes using boundary mode analysis 1 and 2, and then we launch that particular mode using frequency domain in the central domain.
And will there be any application where frequency domain comes first? Because it was by default first.
Sorry, can you come again?
Is there any application where it will come first? Because in COMSOL it was by default the first.
Yeah, no, no, no. Yeah, there is no. If you're using boundary mode analysis or numeric ports, boundary mode analysis would be always first. Okay, if you're using
Okay.
other ports like periodic ports, then you don't need boundary mode analysis. But if you're
Yeah.
using numeric ports, then boundary mode analysis would always be first.
Okay.
Okay, that's how we added the boundary. But first, we added only frequency domain, and then whatever new studies we add, it will come below only.
Sir, as you said that when we do the transverse analysis, we will get the mode. In that case also we have to perform the boundary mode analysis.
No, no, no. That we will do mode analysis only. Yeah. Why it
Why?
is known as boundary mode analysis is because it is selecting the boundaries. Okay, it's the same mode analysis only, but because we are applying at the boundaries, we are calling it as a boundary mode analysis. When we do the cross section, transverse cross section, we will apply mode analysis only. We will
Okay.
not get an yeah, you will not be doing a mode analysis. So here, do we get any option like mode analysis? No, right? Yeah, that is only possible. It's available here, right? So, but mode analysis will not be the correct way to, because we want to do boundary mode analysis. We want to see what are the modes existing in this, and then launch it. So once you see the modes, it will be more clear. Yeah, don't worry. Okay,
Okay.
so are you guys with me? Anyone got lost in the woods? Yeah, that's good. So I hope you are with me. So just click on compute and let's hope we get some meaningful results. So we solve for around 27,000 degree of freedom, which is good number to work with. Okay. Okay. So anyone getting this kind of results or facing any issue?
Sir, this is Jay Krishnan.
Hmm.
I am facing an issue.
Okay.
So instead of using the frequency domain, I used wavelength domain,
Okay.
but I'm getting the modes even in the cladding region also.
So what is the issue that you're facing?
It's like I'm getting the mode even in the cladding region.
Oh wow. So you have used the wavelength over here, right? In wavelength domain,
Yeah,
not the
yeah,
frequency.
yeah,
You can share your screen. Let us see.
yeah, sure.
Looks kind of interesting.
Just a minute, sir.
How about others? Anyone else getting the results? I think Roshan, you're getting the results, I guess.
Getting the same as you,
Oh,
sir.
Sujay also
Yeah.
getting a. Faraz, you're able to get?
So
Yes,
can
I
you
am
see my
able to
screen?
get.
Okay. How to others?
Hello?
Sorry. Oh, wow.
Can you see
It
my
is.
screen?
Yeah.
I'm getting a feel like this.
Yeah. So, can you, because it's so now, can you interpret what is happening from the results? Why it is happening like this?
So the entire leakage is in the cladding. There is
Correct,
no
correct,
propagation inside the core.
correct, correct. So, when will that happen?
The refractive index
Refractive
mismatch.
Refractive
index got
index
lost.
difference.
Yeah. So, let
It's
us try that.
fine.
So, can you show the refractive index of clad and clothing? Cladding.
Yeah, the cladding is 1.
Okay, that
Core
is correct. How
1.5.
about core? This also looks to be
So
correct.
if I go to this
Uh,
recognition,
okay, fine. Yeah, this is go to port one,
yep.
numeric port one. Okay, go to port two. Could you go to port two? Okay, this looks off. Numeric port off. Go to boundary mode analysis. First boundary mode analysis. So here you use
So the frequency is the wavelength used is 1.55. It is also
1.5 micrometer. How much we gave? 1550
Yeah,
nanometers.
that
It's
is a,
same thing, right?
yeah, it was a parameter. Yeah, it is the same
Same thing. So
also.
boundary mode analysis. How about the next boundary mode analysis? Oh, you search for 10 modes. So
Yeah,
you what you saw is the 10th mode, not the fundamental mode. So you don't change anything. Don't run the model. You go to the surface. But you are not. So by default it will. Now you are
no,
correct. Yeah. Go to that. Not this mode. If in effective index to be the last
even
one.
though like this is the first mode actually, but this
No.
also like all
No.
the
No.
modes are
No. The
the same.
problem is that you go to boundary mode analysis again. Go to the next one. Okay. So now you go to this electric field, and what is the effective index of that? Effective index, how much?
Actually,
One.
the maximum effective index I'm getting
Yeah,
is
1.4. How much are we getting? We are getting about in terahertz. Okay, in this one, 1.4029. How about you? Same thing? 1.4029? Yes, sorry.
Sir, I'll delete all the solver
Yeah,
configuration. I'll
yeah.
rerun.
Yeah, can you rerun this?
Yeah,
Yeah, perhaps it was showing plotting for some other modes. But
yeah, yeah,
yeah, but yeah, that's interesting. Uh,
yeah. Now I'm getting it.
okay, Shaibul, face, I have faced problems. Yeah, what problems are you facing with respect to
So
COMSOL?
thank you. I'll stop sharing this.
Yes, yes, please. Shaibul, are you around? Yeah, I think you are not able to hear me. Anyone else facing any problems, issue?
Hi, uh, hi.
Yeah, hi, Satyakosh.
Yeah, I'm getting one error. Can I share my screen?
Yes, please.
So, yeah. So I got this error while computing.
Okay. So the frequency domain is the step one. So it should be step three. Okay, so you can just pull it downwards. Perfect. Now can you run again?
And for me, I have set this
Manual.
manual
By
because I.
default, you keep it by default. Don't change anything as of now.
Okay.
And this search around mode just enable. It's disabled, right? In your case, it
Okay.
should be enabled to 1.5. So otherwise, it will try to keep on searching some. No, no, not that one. Bottom. This one. For both of them, you enable and 1.5. Correct. Okay. Can you show me the material properties again? Okay, this looks good. What about the clad? This looks good. Can you show me the port one settings? Okay, go to port two settings. Okay, so can you just right click on the solver configuration and delete it? Just right click on solver delete. Right click on solver configuration, please.
Yeah.
And
Delete everything.
yeah, correct. Frequency you have kept it as C constant by this one. What is? Oh, here it's wrong, right? Yeah, it should be 1.55.
C constant by 1.55.
Instead of one, you write 1.55. That's it. No need to change anything else. Right. How about in boundary mode analysis? What have you mentioned? Frequency. F naught. That is the same thing, right? C constant by.
Yeah. Yes.
Okay, that makes sense. So only this F naught was missing in your frequency domain. I think then it should work. Here you can write F naught itself, or the same thing. What it is, it should be the same. If everything you change it, everything. Don't write here F naught. Completely here you can make it F naught. F naught. Yeah. Yeah. Now click on compute.
Yeah.
Yeah, makes sense.
I got it.
Sir, I have a question.
Thank you so much.
Yeah, Kavita.
Sir, how you have calculated the refractive index of this mode?
That is effective refractive index I have found. Effective
So
index.
how can we do that?
Yeah, so it's present in this. If you see over here, if you go, so yeah, means I was coming to that. So here, if you go electric field over here, and instead of study solution one, you can go to the study one solution store one. Okay, these two are for this boundary mode analysis. Okay, so if you click on this one, you will see over here the effective mode index. That is for the fundamental mode. Okay, you can also see over here electric mode field. Okay, that is so beautifully showing a fundamental mode, right? So here also you can go to study one store one, and you can find out the type of mode. Okay, for the excitation as well as the ending mode.
So how can I get this? I'm not getting this in my
You're not getting?
slide.
Which
No,
version are
sir.
you using?
5.3.
Okay, so can you share your screen?
Sure, sir.
I can see this, right? 1.4029. That is the effective mode index, refractive index. Can you see yourself? No? Are you there, Kavita?
Sir, I'm saying that electric field plot you are getting the.
Oh, that one.
Yes,
Plot
yes,
you're saying. That is
yes.
and something new that is developed in this one. So if you want to plot it, you need to create a one line plot. So just right click on the results. I will show you.
Right.
I think others can also see, right? So if people
Yes,
are
sir.
not getting this, you can do it. So right click on the results, plot
Mhm.
1D line, plot 1D
Plot group.
1D plot group. Correct. Yeah. Yeah. Right click on this and create on line plot.
Where,
Okay,
sir?
but here it might not be there. So no, instead of this, you right click on results. It will be more simpler way. Yeah. Right click on results and plot 3D plot group. 3D or 2D, sorry, in our case 2D. 2D plot group. Okay. Right click on 2D plot group and select line plot. Okay. Just right click on the 2D plot group and create line plot.
Line.
Yeah, no. Right click on 2D plot group 4, line plot. No, just right click on it, 2D plot group 4. Right click
Yes, sir.
and
Done that.
okay, I cannot see it perhaps. Yeah, line plot.
It's not visible on the screen, sir. Yes, sir.
Yeah,
And there are option of line, contour, streamline,
yeah,
row
line is
line.
there, right?
Yes,
Choose
sir.
line.
Okay, sir.
Correct. Now, okay, so now we have to select that line in the first three. So here we have to select. So you right click on the data sets,
Right.
uh,
Okay, sir.
and then click on edge. I think edge will work. Edge. No, not edge is not working. Edge 2D, is there something more data set? Edge 2D.
Yes, sir.
Edge 2D.
H2D is there. Yes,
Uh,
sir.
Choose edge 2D and select
Mhm.
the first three boundaries where you apply port 1. Yeah, that's good. Just okay, that would be too complex, but yeah, manually you could select all these 3 domains. This is 1, 3, and 5. You can remove the other one. Just keep 1, 3, and 5. Yeah. Yeah. Now go to that line plot again. Yeah, and select this H2D one
Where, sir?
in the data set from parent. Instead of from parent usage H data one.
Nothing is there, sir.
That's fine. Now you need to search
It
for
is
the
there.
expression.
Only the view is different. Yeah.
Yeah, it's correct. No, correct. Yeah, that is true. But what you can do is just but yeah, no, but one more thing is remaining is that actually if you just right click on the line plot, just add height expression. Right click on line plot, height expression. So what you're plotting right now is not for the boundary mode analysis. You're doing for this frequency domain. If you want to plot from boundary mode analysis, you could go to line one. Okay, line one again, and change the expression here, search expression, and you have to search for the boundary mode electrical field. No, no, not there. These are green and red buttons are there, right, on the right hand side. Over here, just search for uh, boundary mode, tangential boundary mode. So these are the tangential boundary modes. So just write boundary, search for boundary, and you will get something like EBM, tangential boundary mode EBM.
So which I have to select tangential boundary mode field
EB,
X component, Y component.
tangential boundary mode electrical field. There will be norm EBM
Yes,
underscore
sir.
one.
Normal
That one
component.
please
Yes, sir.
select. Yeah, yeah, normal. That you select, and then you can. No, no, not this one. Actually, there is one more. So I can share in your. I've shared in the message box. You can just copy paste it, and or you can just search this thing EBM
Sure.
underscore one. Yeah, so that you can just select. Okay, so it would be based on that particular modes. Okay. Okay, looks good. So anyone has any other questions?
Hello,
Yes,
sir.
Yeah, Shaibal.
Yes, sir. I am facing some problem during computation.
Can you share your screen, please?
Okay, sir.
Okay. Fine. Can you show the material properties? Here, material
Yes, sir.
properties. Core. Okay, this looks good. Go to clad. This looks good. Can you go to port 1? This looks good. Go to port 2. This looks good. Okay, so here frequency domain will come to step 3, not first.
Sir, how
Okay.
can I change that?
Yeah, I just just grab it and pull it down. Yeah, just try it once more. No, no, you're pulling it so much down. It should be between step 3 and solver configuration. Yeah, this one. Now drop it. Yeah,
Okay,
now
sir.
you can start to run again the model. Yeah, rest of the things I think it's fine. Should not be a problem. Okay, so this should work. Anyone else having
Yes, sir.
problem?
Uh,
Yeah, hi
I'm,
Fatima.
yeah, I'm facing the
Okay,
problem
sir. Thank
in
you.
simulating. Shall
Yeah,
I?
yeah. Please
Can
share
you?
your screen, please. Yeah, you can mute Shaibal if you. Okay, looks good. Thanks. Fatima, you can share your screen.
So yeah, maybe I've done something wrong with the
Yeah, yeah,
computation.
there's something terribly wrong. So go to table port one. Let us see. Let us try.
Oh,
And I think it's good for everyone to see because at
hmm.
some point of time we all may do the same mistake. So that's good actually.
Actually, I missed out on the initial part, so I tried
Okay.
to do it on myself. So.
Okay, looks good. This is good. So port one is looks to be. So type of port should be numeric. Okay, type
Oh,
of port.
yeah.
Yeah, this should be
Okay,
numeric.
mode.
Port two should also be numeric. You're launching actually mode electrical field to be zero. The user
Yeah,
defined zero. That's why it's.
I changed it right now. Initially, it was
Okay, okay. So
okay.
rest of the so can you
Now it
show?
should work.
Now it should work, right? Okay. Now you can run and
Should
see.
I build the mesh again?
You don't need to build the mesh again. This
Just
I just
complete.
do it just to show you that how it works. Yeah.
Uh, it's not okay.
Yeah, it's happening. Just wait. Okay,
Yeah,
looks good.
thank you. Sorry.
No problem. Yeah. Yeah.
Sir,
Anyone?
sir,
Yeah.
I
Hi.
can.
Yes,
Yeah,
sir.
myself. Yes, sir. Myself is Japan. I'm not able to run that. Can I share my screen?
Yeah, please.
Whether my screen is visible, sir?
Yeah, yeah. So can you? Okay. You change the mesh settings. Go to mesh one. Yeah. Use physics control mesh, not user control mesh. Okay. You don't want to play around with the mesh. Port one. How does the port one look? That looks okay. Good. Port two. This also looks good. Go to boundary mode. Step one, go to step one. How does it look? Step one, boundary mode analysis. Yeah. Just left click on this. So here the frequency should be F naught. Have you defined this frequency in
No.
parameter? Yeah. So mode analysis frequency should be F naught and search for modes around 1.5.
Where, sir? In mode analysis frequency.
Here you write F naught. Or instead of 1, you write 1.55. No, not here. 1 micrometer is then 1.55. Then search for modes around shift is 1.5. Come down. Yeah, search for modes around shift. Can you see? Search for modes around shift.
Where,
Above,
sir?
above, above, above. A little bit more above. Yeah,
Uh,
yeah. Just enable it. Just search for 1.5. Do the same for boundary mode analysis too. Yeah, search for modes around above, above. This one. Then frequency domain. Sorry, not 1.55. 1.5. Did you do the 1.5 only right before?
yes, sir.
Go to frequency domain. Here, write 1.55. Okay, and then run the model now. Yeah, just compute the study two. Right click on this or just go to the study to compute. Okay, so hopefully this should work. Anyone else facing the problem to get these results? I think Roshan, you had raised your hands. I think you're getting the results, right? Okay. So you are facing one more issue. So undefined value. So can you just right click on solver configuration and delete?
Which one, sir?
Just right click on solver configuration, right click on solver configuration and delete configuration. Yes, yes. Uh, yeah. Okay. Just go to the material section again. Material. Okay. Clad you've given 1. So actually it should be 1, 1.4, not 1.4, should be 1. Clad, the value. Yeah. Put it 1. 1. And the core you give it 1.5. 1.5. So yeah, this was like very tricky for COMSOL to find out because Now you study to go to study to and compute again. That's why if you go to the convergence plot, you will see that how are you faring. It says convergence plot 1, right? Yeah, you can go to that, click on that, and you can see. See, still it's not converging. Okay, go to the boundary mode analysis again. Are we missing something here? Yeah, go up. Okay, go to boundary mode analysis 2. Did you change anything, or it was by default only
No,
this
I
type?
not changed anything.
Okay. No problem. I will just take it again in one-on-one session. This thing, okay?
Okay.
Yeah, you can see this uh, recording as well. It should
Okay,
not
sir.
be a
Okay,
Sir,
sure.
Sir,
excuse me,
in
sir.
port name, he kept it as 1 only in the
okay.
boundary
Okay.
condition.
Yeah, yeah. So, it's okay.
Sir,
Yeah. Can you change that port name as 1 and 2 in boundary mode analysis? So first should be 1 and second should be port 2. Okay, and then try to run.
can I repeat, sir?
Can you share your screen again?
One second.
Yeah, so go to boundary analysis 2, second. Here you need to change the port name to 2. Okay, now you compute. Your battery is almost draining down by COMSOL simulation, I guess. You'll survive only for 12 minutes. I think, yeah. So now I think it's solving. So you're not able to see the results because go down in the result section. Yeah, just right click on solver configuration once more and delete it and then run the model again. Which version are you using right
Six
now?
point something. 6 point. You send me email, right? That version,
Okay.
14 days trial
Okay.
versions.
Good, good. So go to study 2 and compute again. Yeah, looks good. So
Thank
I
you,
think
sir.
that was the only problem. Yeah. Looks good. So I think that's good. So anyone facing any other problems in COMSOL?
I have a question,
Mm-hmm.
Uttam. Maybe since we have just only 5 minutes remaining, so I'm not sure this is the right time to ask you. But
No problem. Go ahead.
okay, so my answer, my question is that since we achieved this plot, so what are the? Could you please interpret that
Yeah, yeah.
what we are?
Correct. Yeah, yeah. That's a good question. So I was coming up to actually that one. So now coming to the interpretation part of the result. So here you can see that I don't see where it gone. Okay, I think it should come now. Yeah, looks good. So now again, you see that your wavelength is 1.5 nanometers. Sorry, 1.5 micrometers. So here you will see around the peak to be around 1.5 means one wave will die down over here. There is one more over here and over here. So around 3.5, almost 3.3 third would be the wave that you can see, and that you can see by plotting the z component of E field. So you need to plot the EWFD dot EZ. Okay, so here you can see, right? So it's starting over here. This is first wave, second wave, sorry, third wave, and then the fourth wave. Okay, and so this is how the electromagnetic wave is propagating. And again, if you want to see how it is propagating, is just click on the animation in player, sequence type as dynamic data extension, repeat as forever, and then just click on play. This is again is very important to see the animation always, so you know that things are working. You can also see the scattering parameters again over here. You should it should be kind of 1 and 0 almost, because there is no lossing material.
So can we also check that the plot, electric field plot?
We are plotting the electrical field plot only. Means you want to see
So
This one.
in form of curves, like value, we should know that near the core we should have
Okay, okay.
the
We want to do
highest electric field strength.
So for that, what you do when you to create one line plot inside. The way to do that is just right click on the data set and create one cut line 2D. If maybe I'm running too fast, I don't know. So let me just ask: are you guys able to create this animation? Anyone facing this issue of creating animation, because that is crucial part of modeling. You should see that there are no reflection, with no kind of problems while you run the animation with the dynamic data extension. Anyone facing issue with this animation? Okay, looks good. So I hope that you are not able to face any
Hello.
problems. Yeah, sorry.
Yeah, so Pratik sir here.
Mm-hmm.
Yes, sir. Actually, I am facing problem. Like it is showing when I'm clicking the play button, an animation must contain at least 2 frames.
Yeah. So here, did you change it to sequence type as dynamic data extension? And if you change it to this, it will change to the number of frames as 25. By default, it's
Okay.
25.
Okay. So where I can change it?
Sequence type. This is
Oh.
for 0 to 2 pi. Okay. It'll be based on different phase of launch.
Mm.
Sir, how did you get the current plot of the crust and trough that you are showing? You did a 2D plot,
Yeah.
right?
So
Not.
no. This is same thing. Instead of norm E, I plotted Z component of E field, out of plane field. Z component of E field, EZ. I'll just share with you guys as well. Okay. So EWFD.EZ I am plotting.
Yes, sir.
Sir,
Got it.
can you show the animation 1 frame once more?
Yeah.
Yep.
This is the animation.
Yeah.
I've changed only dynamic data extension. Only this is changed. And then I've
Okay.
changed the
Stored
repeat
solution
forever.
to dynamic. Okay.
Mm-hmm.
Got it.
Repeat forever.
Yeah. It's now right.
Hmm.
Thank you, sir.
Okay, looks good. So next thing is to see the electrical field in a 2D plot in the center. So that way would be just right click on the data set, cut line 2D. Okay. Once you have the cut line 2D, always good to just click on plot and see where are the cut line. So it will be in the center. Okay, that is one of the reason why you try to pull everything into the origin, especially in the propagation direction. So you need to know that it need to be extended to 5. So the red line that you see is that where you are probing.
So if it is not in the center, then what should we have to do?
Yeah, just hold on. Just hold on. Yeah. So what was your question? Sorry.
So in my structure, when I have chosen that cut line 2D, there is only option of 0 and 1. When I clicked on plot, the line is not in the middle, it is below in the lower section.
Okay, okay. Then you need to pull it above over here, or you change the geometry. Any of that is fine. Okay, so for example, it is why I want to pull this down lower, then I change my wide 0 to, so this is my starting point, this is my end point coordinate. It's a line segment, right? Starting coordinate and end coordinate. Okay, starting coordinate is 0 comma 0, 0 comma 0. Okay, end coordinate is 5 comma 0. You understand what I'm saying, right?
Yeah. Okay, sir. Okay, sir.
So you can pull it downwards by making it as, for example, or pull it upwards by changing my y. So starting point is, for example, I want to have line segment over here in the top. So I put 0, comma 1 and y, comma 1 and then pull it upwards. This y you need to play around with. Okay.
Yes, sir.
Now I need to plot what is the electrical field at this particular line. To do that, I just right click on results, 1D plot group.
Hello, sir.
Yeah, hello sir, tell me.
Sir, I have this issue.
What issue you have?
Cut line 2D.
Okay.
The line is on the top.
Okay, it's in the top, right? So you can pull it downwards or upward based on changing the Y position. Okay, so you can make it downwards by putting appropriate values.
Okay, sir.
Okay, so you can pull it downwards by changing the value of Y.
So
Okay.
there is
Okay,
no
sir.
plot coming.
Okay. Anyway, I will just discuss with you in one-on-one session then. No problem.
Okay, sir.
Let me complete this part. So I hope you have added this 1D plot group 5. That is, just right click on results 1D plot group, and then right click on the 1D plot group, and then click on the line graph. Okay. Once you click on the line graph, you should get in the dataset as cut line 2D1, the one that you created just sometime now, and then you just write EZ over here and plot. Okay, so there you are actually getting the electrical field, how it actually looks. So what, same thing what you have done over here, right? But now I have a line segment in the center, and now I can actually visualize it in terms of 1D plot group.
Yes, sir. I've done the same thing, but not getting this plot.
Okay, no problem. So we'll see in the next session then. Okay, let us take a break of 30 minutes, and then at 5 o'clock, let us start again. In the session, we will also talk about the cross section, transverse cross section, and mode analysis of these optical fibers.
Okay,
Okay,
sir.
that's good. Thank you.
Really?
Is anyone speaking? I'm not able to hear anything.
Hello and welcome everyone for the one-on-one discussion. Should we start the session now or should we wait for people to join?
Hello, sir.
Yeah, hi, Shaibal.
Yes, sir. Now, last time you saw that the electric field, the mode in which way the mode propagate, we cannot find that.
Okay, so were you able to create a cut line?
Yes, sir. In the middle.
Yeah. Were you able to create it?
Okay, sir.
No, I'm asking, were you able to create a cut line 2D
Yes,
one?
sir. Yeah, 3 minus 3.5 and minus 3 minus 3.5.
Okay, so did you create one D plot group then?
No, sir.
Yeah, so you need to create a 1D plot group by right clicking on the results. So I'll just share my screen.
So, can I share my screen?
Just first see what I am doing and then you can
Okay, sir.
try
Okay,
it
sir.
out. So,
Okay, sir. Okay, sir.
I hope you have created this cut line 2D one. Can you see my screen?
Yes, sir.
Yeah, and then just right click on the results and create 1D plot group.
Okay, sir.
And in this 1D plot group, just right click again and click on the line graph. Okay,
Result
this
1D plot
line
group.
line graph.
1D plot group, then right click.
Yeah, line graph. You can see
When
my
I click
screen.
1D plot group, then okay, sir.
Yeah, just once you right click on the 1D plot group, there's a line graph. Just select on that line graph.
Only product line graph. Okay, sir.
Yeah. So in that parent dataset is there, right? Can you see my screen dataset? Instead of from parent, you use that cut line that you created some time back.
Dataset cut line 2D.
Yeah.
So try. Cutline 2D. Cutline 2D 1.
Yeah, yeah.
Okay, sir. Then plot.
Yeah, and then instead of expression norm E, you write EZ,
Okay,
and then
sir.
click on plot.
Okay, sir. Now you got it.
You get it? Okay.
Thank you, sir.
Mhm. So any questions till now?
Hello, sir.
Yeah.
Yeah, I'm getting a different plot, not the one which I see in your screen.
Is it the cut line at the same place where I am showing over here? This cut line, is it, if you plot it, is it in the center?
Cut line.
This red line, is it in the center of your domain?
No, sir.
Yeah.
In actually in cut line, I don't get anything.
If you click on plot cut line, you don't get anything. You click
Yeah,
on
I
plot.
get, I get, I get, and the red line is at my center.
Sorry, your center from 0 to 5.
Yes, but before 5, there is a cut.
Yeah. So make sure that is 0 and 5 over here. So this coordinate is 5 micrometers, comma 0.
Yes, sir.
Hmm.
It
Just
is
make
0
sure.
and 5. 0.10, 0.25. Yes.
So now it is completely covering this. Yeah, you can share your screen, no problem. I will just look into it.
One second.
Mhm. You can share your screen so I can just look into it.
Sir, I am also not getting plot.
No problem. We'll check into it. So Padmapriya, are you sharing your screen or Kavita can? Okay, I think you're sharing. Good. Okay. Okay. So now that looks good. So I can see that. So can you go to your 1D plot group now? Oh wow. No, go to line graph one. Yeah, so you need to plot EZ, not norm E. So norm E is like it's kind of showing that it is almost like very high values. So norm E instead of norm E, you need to write capital E and Z. I think you are muted, so we cannot hear you. But yeah, you can just capital E and small Z.
Yeah, I'm doing so. 1 second.
Mm-hmm.
Capital E and small z.
Mm-hmm. The Z component of E field that you're trying to plot.
Okay. So I have
Then click
changed.
on plot.
Okay. Yeah, I got it.
Mm-hmm.
So I had one more problem.
Mm-hmm.
During that animation, no?
Mm-hmm.
Here also I was not
Yeah,
getting,
yeah. So
yeah.
you need to write again EZ. In electrical field EWFD, you need to write EZ.
Where I should write?
In
Oh,
the below
here.
the table. No, not here, not here. On the result section, left side,
One
electrical field EWFD is there, right?
result.
Down, down, down.
Hmm.
Below this one. Open that.
Hmm.
Yeah, no, no, open means that uh, triangle is there now on the left hand side. Open that node where I can change the settings inside it. Means which expression I want to change. There is a small triangle on the left hand side of electrical field, right?
Yes.
Yeah, go inside that.
Uh,
So click on
Surface.
surface one.
Okay.
Here instead of norm E, you need to write capital E, small Z.
Okay.
Okay,
Plot?
now plot and then again see the animation. You can run
Is
the animation again.
hmm.
Yeah.
I should give show frame.
No, no, no. The run the animation. So if you do show frame, what will happen? No, no. You just run the animation on the below graphic. That one, correct. Play.
Yeah, got it, sir.
Okay.
Thank you.
Yeah, looks good. Yeah, Kavita, you had a. You can share your screen, perhaps.
Yes, sir, sharing it.
So can you show me your cut line one? Just how does it look like? Cut line 2D one below the data set. That one. Just plot it. Yeah, so here the data set should be study one, solution one, not study one, store two. Yeah, so this would for the boundary mode analysis. You're not solving for the boundary mode analysis, right? So you will get 0 over there. Okay.
But sir, when we study the electric field inside the core, it is having the high peak. Only a single mode is propagating here. So instead of multiple peaks, shouldn't we get only the single peak?
Yeah, I mean, if you show the normalize, then you will see, but it's not fluctuating, right? So the electrical field will not be constant. Electrical field component is that component will fluctuate. Not the magnitude will be constant, but it's actually fluctuating, right? So
No, sir. The thing I'm asking is if I have only single mode, if I'm considering the fiber I have designed in the 2D is a single mode fiber,
hmm.
there will be only the propagation of a single mode. So
Yes, this is
instead of
single mode only, but this is like along this with respect to the how it is propagating. For example, you go to electrical field now, electrical field EWFD surface one plot. No, no, not here. That one, correct. Yeah. So what you are doing, you're just putting one line in the center, and
yes,
you are
sir.
plotting it. So
Yes,
that's what
sir.
you're doing right now.
Okay, sir. And for getting that single peak, what should I have to do?
That in 2D plot group is there, na? That line plot that you have done. Yeah, this one. But I think you have changed it. So you need to make it to edge 2D one. Instead of cut line 2D one, you edge 2D one at the border. Yeah. And then
No,
enable the
sir,
height.
this is not the question I'm asking.
Mhm.
I'm asking if I have to have this transmission kind of plot, and instead of this, I want to show that by varying the radius of the core and the cladding, the electric field propagation, there is evanescent wave in outer boundary पे जो भी evanescent wave propagation
Uh-huh.
will be there in the cladding, and
Okay,
then
okay,
we
like
have the
that.
peak.
Okay, okay, I understand. So then, in case you need to, so I will show you what you need. So if you see my screen, I will share my screen. So what you need to do is you need to create one line segment over here. Okay. So example, if you just right click, again you create one more cut line 2D. Okay, and I want to plot it across this domain over here. So for example, I do this line segment starting from this point around 2 comma minus 2.5, and point 2 could be like 2 and then plus 2.5. So this, okay, sorry, what about why is it? Okay, yeah. So it's along this line, right? So along this line I want to see how is my electrical field surviving, right? So I
Yes, sir.
create this cut line 2D1, and then I again create the same thing, 1D cut line plot group line graph, and here I choose the next one that I have selected, and here I plot the norm E, for example. Okay, so here you can see how the field are dying across
Okay,
this
sir. Okay,
thing.
sir.
Now you can also, as you said, you can also run this parametric sweep of
Yes,
changing.
sir. So that
Uh,
how with the distance of core
yeah,
we are wearing that field
correct, correct.
profile.
Yeah,
Okay, sir.
correct. So you need to do a transverse cut. What you have done was a longitudinal cut. So you see that it's fluctuating, right? So
Okay, sir. And this I can do at any distance.
yeah. So unless until you're plotting this norm E,
Hmm.
If you plot Ez means that based now it becomes based on the phase,
Hmm.
whatever with the respect to the phase you're talking about, then it will come. So if you put the norm E, then it is irrespective of the phase. You understand what is phase I'm talking about? So here
Yes,
you
sir.
see that here it's increasing. So
Yes,
if
sir.
you put over here, it will be a negative thing. For
Sure, sir.
example, if you were here, so right now I was surviving over here. I
Hmm.
put a line segment over here, so it was showing. If I put over here, it will be negative Ez. For example, 1.8. Okay, I will show you. This is for 1.8. It is having a negative peak. Right. So instead of the peak, I will get a negative line over here. No, I'm not getting. Okay, sorry, I'm plotting is norm A. Here you see, right? It's a
Yes,
negative
sir.
line.
Yes, sir.
So if
Yes,
you
sir.
plot this animation, you will see that along this line, because it's a fluctuating guy, so it'll keep on fluctuating up and down. And
Oh,
so
that's
along this
great, sir.
line, I'm
Yes, sir.
changing my phase dependent animation. So based on the phases, it's like fluctuating at that line.
Okay, sir. Okay, sir. Got it, sir.
Yeah.
Hello, sir. This is Govind. I
Okay.
have a question regarding when you are calculating this electric field,
Mhm.
and I wanted to know what is the input power for that particular mode, and how we can calculate that input power for that particular core, how much power in the core.
Yeah, yeah. So if you see the port one, by default you give 1 watt per
Yeah.
meter. So here per meter means because it's out of plane. So it's actually out of plane is infinite. So it's if you have 1 meter, then it becomes 1 watt. Okay, so it's with respect to this meter cross section. So anyway, so the power way is one way is to find the power is to, so you're giving 1 watt for example.
Mhm. So my question is, 1 watt is within the core, or it is going to core and clad region, right?
Both the whole power is 1 watt. So now for
Yeah.
example, I want to know what is the power which is being flown in my core region only, right? So what I can do is I can make this y to be around zero point 0.5 and this guy would be minus zero point 0.5. So I have a cut line only at this point. Okay, so what I can do, I can do a integration of my power flowing at this line segment. So how do I do that? It's just right click on my data set and I can create a
That I know means integral. By doing integral, I can get that power in that particular core. Now, if I want to know how much power in particular mode, then what I have to
so
do?
right now you're only working with fundamental mode. So you talk
Suppose
about
we
the
have several modes. Then
so that we have to first find that particular mode. Now where is the
Sir,
integration?
can you please explain that integration wala part?
Yeah, yeah.
Possible.
So I'm just trying to search where the integration guy went. So it's where it goes into the derived values. So just right click on derived values and you see this integration part. So you can do a lot of integration. As of now, it's just
line
a
integral.
line. So I
Yes.
can use a line integration. Uh, okay, and I can choose this cut line 2D1, and what I want to integrate over, I want to integrate over the power. So how much power is flowing in my x direction, because my energy is flowing in x direction, so it has to be this one. Okay, so we can see over here. So around 0.92 watt per meter is 0.92 watt is the amount of energy which is flowing at that particular region. Okay, so there could be some kind of losses itself. Uh, this line segment you can also shift it to the right hand side and see how much power. For example, now at 4, now my cut line is at 4 for example, and now let me see how much is my power. So it's like lossless, so it's almost the same 0.92. Okay, now if I put some kind of lossy domain, then you can see
Uh,
that power is actually reducing.
but sir, this is not lossy, right? Core and clad means some power is going in the clad region.
Correct, correct, correct. Yeah,
Right.
because we're integrating only in this small this region, so rest of the power is actually getting lost in the clad
So, is
clad.
it possible to calculate the power in the cladding in the similar
Yeah, yeah.
fashion?
Same way you can just make one line segment and just remove the central region, and then just add both of the power.
Okay. Now, how we can calculate the power for particular mode?
Yeah,
Suppose
yeah.
we have several mode.
Yeah, so for that we need to go step by step. That is so anyone has this question till now about what we are doing? Maybe it's kind of little bit fast for few of the people. Then I will go to jump to the higher mode analysis.
Uh, Uttam, I just have a question. My name is Faraz.
Hmm.
Yesterday, you told about us about the, as we already know about the S parameters. So
Okay.
here, since we know that
Yes.
there on the left side we have port one, on the right side
Hmm.
on we have port two. So just for the sake of simplicity to understand the thing from basics,
Hmm.
let's say I want to know the S21 parameter. Okay, so
Yes, yes,
how we
you can
can
do that.
calculate
So here, just because you till the time you're using ports, you are always safe to calculate scattering parameters. To do that, just right click on derived values and click on global evaluation and just search for S21. Okay, and then just do the absolute and then square. You just write transmittance and then you write for reflection.
which one I have to select? I am getting two S2. One is
So
S21
with
and
yeah,
S.
S21 is the one with without dB, the normal one,
Okay, okay.
and then just evaluate, and you can see transmittance is almost like one because the loss less medium, and
Sorry,
reflection
a
is
bit.
almost. Hmm.
Sorry, a bit. I lost a bit because when you clicked on S21 and then I am getting EWFD.S21,
Yeah,
and so here, but on your screen I am seeing that you are getting ABS.
yeah, no, no. ABS have added. By default, you
Okay.
will get only EWFD.S21 is because the
Yeah.
absolute value is in the square of it. That's
Okay.
how we define the transmittance, right?
So it is in the
Okay.
case of optical structure we have to define the transmittance.
Yeah, correct. Yeah. So in the case of optics,
Sir,
that's how we define. Correct. I mean, in the case of RF, they work more on dB, but in optics, we usually work in this absolute and then square of it.
So what does it
uh,
signify here that having the absolute value here? Is there any
Uh,
significance or just
mm,
for the calculation purposes?
so the imaginary part of this S parameter usually is with deals with the losses. So taking absolute value combines all this power. Uh, yeah, that could be one of the reason. So yeah.
sir, this is Jay Krishna. I have a doubt.
Uh-huh.
Sir, if you go to the derived values, there we can see the reflectance, transmittance, and absorption.
Okay. Mm-hmm.
So here also they have different expressions.
Yeah, it's the same thing actually.
So, like
It's
both the
internally
expressions are
defined
different,
the same thing.
right?
Internally, it's defined the same thing. The same thing what
Okay.
we are doing. Internally,
Okay.
this they have defined new parameters, but people were asking where is this transmittance port. So rather than writing equations, they want directly the transmittance and reflectance and absorption. But internally, it's just the same thing. Okay.
Okay.
So could you please go back to the equation where you put the okay,
Yeah.
and
So I
here you
shared
yeah
it. Yeah.
here
Silvi.
you have put S11 in the second and S21 in the first.
Yes.
So could you please elaborate a bit about it? That why you put S2? I know this S21 is the put, but why S11?
So absorption is represented by which parameter?
Absorption is defined. So let me go one by one.
Sure.
So the scattering parameters question first was why S11. So if you remember yesterday we talking about a two-port network system where your port one is input and port two is output. The way how S parameter is defined using SAB, where A is the output and B is the input, right? So when you write S21 means your output is at 2 and input is at 1, means how much power is being thrown out from the
Okay.
system. If you mention S11, it means what is the output from port 1 when you give an input from port 1, right? So S11 signifies the what is the reflectance, right? So if you take the absolute values and square it, then it gives you that reflectance value. If you make the absolute value of this one and then square it, it becomes the transmittance. So this mainly these two are of these scattering parameters are usually used in a two-port network system, assuming you give an input at one. We don't give an input at port two, right? So that's why we don't use these two parameters.
Okay, and when I click evaluate, so I will get the values on the bottom right, I think, right?
Yeah, in the table you will get it.
And how we can interpret these values?
Yeah, so transmittance if is one, right? So means it's full transmission. So maximum is one. So this value of TNR is between 0 and 1. So reflectance is almost 0, means this very less reflectance coming out of it here. Okay.
Okay.
So all the energy that I am giving, everything is being transmitted. There's no reflection. Okay.
Okay,
And
but this is the ideal system. This is not the
correct. This is ideal system. So we can just induce some losses. For example, in the core, I can induce some losses. For example, 1e minus 3, and then I run the model again. Okay. So the first thing that you will see is this. Uh, can you see anything? Maybe the losses are not much significant. Let me write 0.1. This is a significant loss. I don't know. Yeah, so now we can just to make it more visualizing, appealing, I just added more losses. So here you can see how the field is being exponential loss kind of thing. You can see, right, or linear loss. I don't know, and you can see the animation how the losses are happening. So you're putting so much energy, but it's being lost once you go inside this system. Okay, now you want to quantify the absorption. So you can now again see the transmittance and reflectance. You can see that your transmittance is only 0.01. Reflectance again is kind of 0. How do you define the absorption? Is like 1 minus, and you just sum both of them. 1 minus t minus r. So this is the absorption. So it's like around 0.98 is the absorption. Okay, reflectance can almost 0, and transmittance is like very less.
so absorption here. So it means that the energy is getting absorbed, right?
Yeah,
Most.
getting absorbed. Yeah, correct. Here also, if you see, it will be almost the same thing that you will see over here, 0.98 absorption. Okay, that's good. So, any more questions in regard to this one?
Sir, whenever we have the absorption in case of optical fiber,
Okay.
sir, is it like that the the electric field which is propagating it is not reaching to the terminal point?
Yeah, so there are two kinds of losses that we can define with. So one is the so one way to define the losses would be the one that we are doing, that is material losses. Okay. Another way to quantify the losses would be the using mode analysis. So if you do a mode analysis, again you will get imaginary value which resembles the uh, dampness of your system, or something like damp z. Okay, so that would be having a attenuate, so you kind of attenuation constant you will get. So even though you don't need to model the whole propagation, but the absorption that you are saying right now over here, right, so that could be approximated using that attenuation coefficient. So you can find out that beta value, that is attenuation coefficient of an optical
Is
fiber.
it possible to calculate the beta value through COMSOL,
Yeah,
or
mode analysis, you need to do mode analysis.
and then I
That
can directly calculate that?
yes. Yeah. So there is an example over a fiber simulator. If you are interested, you can go that fiber
Sir, I have
simulator.
studied that but didn't understood it properly.
Okay. Yeah,
I
so
tried
fiber.
to understand that, but I didn't get to
Yeah,
know
so
what
we
the
can
features
look
are
into it
explaining
today.
that.
Yeah, in the end. Yeah, no problem that. So you will get this when if you do mode analysis, you should get the beta. So you can see not this beta. This would be something else. Damp Z. So do we have damp Z here? No, it's not here. Yeah, but if you open that fiber simulator model, so it will be talking about this damp Z. I can show you it in the end if time permits today. No
Hello,
problem.
sir.
Okay.
This is Jay.
Okay.
Yeah, sorry.
Sir, this is Jay Krishna. I have a doubt.
Mm-hmm.
Hello.
Tell me.
Hello, sir. Can you hear me?
I can.
Yeah.
Can
Sir,
you hear me?
I was.
Yeah.
Sir, your
Yes.
voice is kind of breaking.
Oh, sorry. Yeah, please
Yeah, I
continue.
can hear
I
you
can
now.
hear you.
Yes, sir.
Okay, looks good.
So I was trying to solve a paper, a PCA photonic crystal,
Mm-hmm.
a PCA fiber. Okay, so in that, so the graph, which is actually the graph between loss versus wavelength.
Okay.
Yeah, in that graph, when I was trying to solve it in COMSOL, so what I have to do is I have to manually extrapolate the ineffective values for each and every mode. Then I have
Okay.
to give the ineffective imaginary part of the ineffective values and input to an equation. Then I have to calculate the loss. So is there any other way like this like calculating this S parameter? Is there any other way for
No,
calculating
no,
the
no, no.
loss?
That is the only way. So that's what I was saying. The damp z variable that itself is the uh, complex part, I mean the imaginary part of the effective refractive index. So if you I don't know, have you seen this COMSOL wave optics module reference manual? Have you seen that anytime? So it actually discusses the in these things in more detail. If you go to the COMSOL wave optics module user guide, okay, over here you will be able to see. Once you do the mode cross section analysis, that is mode analysis, so then
Yeah.
this parameter will pop up. Okay, that is the same thing of this one. So even now actually we should yeah, anyway, so here you can see that this is the attenuation coefficient. So you have the alpha value which is equal to j beta, and then this imaginary parameter actually leads to attenuation coefficient. This is what you are actually
Yeah, looking for.
yeah. So with this you can actually find out, just multiply with the length and then you get this attenuation actual, right? So
Okay.
yeah, so
Sir, I have a query.
uh-huh, yeah,
Instead of single mode fiber we have discussed right now, if I have the multi-mode fiber,
okay.
then how can I see the multi-mode propagation inside that? And out of that multi-mode, which mode is having which absorption or transmission coefficient? How can I calculate that?
So first thing is yeah, it leads to the which mode will it exist. So you have to search for which mode it.
Because as it is
Yeah,
a multi-mode fiber, there are number of modes present there inside the core.
yeah, yeah.
Then
So I
how
think
can I
have you
interpret that?
seen this example with multi-mode? One fiber example is there. It's a newly established example. I don't know have you seen that or not, but in that we talk about multi-mode. No, not we, means the COMSOL talks about the multi-mode. Is a waveguide. Yeah, so here you can see there are few of these multi-modes
So these are
fibers.
microstructured, but there are
Okay,
silica holes inside there.
okay,
These are
okay,
not
okay,
multi-mode. These are
okay, okay.
microstructured fiber.
Microstructures, okay.
Yes, sir.
So even it is in case of multi-mode, what is the challenge that you are facing?
So currently, I'm not able to see how many number of modes are inside the core or outside the core. First challenge is that. Second is I'm
Okay,
not able to get the plots I have got right now in case of single mode fiber. The variation is not clearly defined in that case. That
okay,
which mode I'm getting and which mode is the propagating one
okay.
in
So
the core.
I can once I do this example of multi-mode, I can I mean a single mode fiber. We can see over there how it happens.
Sure, sir.
Okay.
Yes, sir.
So yeah, so that brings the question to the next mode, high to search for higher order modes.
When I have to search the number of modes in case of multimode, if I take five or four or three or
Yeah, yeah,
two,
yeah. That I
whenever I
understand.
do that,
It's very difficult.
sometime it
I
is inside
understand.
the core, sometime it's outside. When I'm not
Uh,
able to explain it to the
yeah.
other
Mhm.
person that why it is so. And
Yeah.
similarly, in case of search for the modes around shift, if I'm choosing the encode, then the results are different. If I'm
Yeah.
choosing inside the around the cladding,
Mm.
then the answers are different, and there
Correct.
is no explanation about it that why it is happening there.
No, so what happens because you are doing eigenfrequency analysis. These all are thing eigenfrequency analysis. Now, in those cases, you sometime need to search for hundred of modes
Sir, I
Okay,
have done the mode
and then
analysis.
yeah,
Then,
yeah, but then what you need to do is that you also need to search for which are the modes which are of more interest. Okay,
then
so
how will I decide? Because currently I
yeah,
don't
yeah,
know.
I will
I
show
just
you.
know that I have to
Yeah,
see the mode propagation inside the multimode fiber. That's my
yeah, but
concept
it's
right
a
now.
cross. Which kind of cross section are you working with now?
So
Vertical or
simple. The cross section which we are using right now, similar cross section I have used. Similar.
yeah, yeah. I think we had done with shown one of this example in one of my blog. I had tried to show the same thing. I don't remember which blog is that. But in that blog, I'm trying to show you actually what is the technique that I tried to use to know, because there are hundreds of modes, right? You want to know which
Sir,
mode is.
if I say that I have to search
Yeah.
only five modes are propagating inside the fiber, let's say,
Hmm.
then
Hmm.
out of these five, should all the five will pass through the core or
No, no. So that's
cladding,
what.
or
See,
what will
if
happen?
yeah, that's what. If you see my screen, okay,
Okay.
this is one of the example that we were working with, and if you see here, I have searched for 50 modes. Okay, so now what I'm doing here, I'm doing a integration of the place where I'm trying to search for modes. Okay, and when the power is kind of very much higher, so I put a threshold. Okay, so here the if I draw this power integrating on that particular region where I think it's more, so the one that is going over there here, right? So at those
Sir,
are
I
the
have
places
not
where
understood this point very well.
yeah,
That's why I'm not able to grasp it
yeah.
completely.
So here what I'm doing, so what I will recommend is that you go through this example, okay, because explaining this will again
Sure,
take
sir.
a
Sure,
lot
sir.
of,
I'll go. Yes,
you
sir.
can, yeah. So here you try to see this filter, like how to apply this filter, and reference one is this John Plus, but I think this is example is which one? Yeah, you can see this example, the one that what I'm talking about here, modeling a photonic crystal fiber. Have I given this example here or not? Photonic crystal fiber crystal fiber block model. Yeah, this one I guess. Yeah, this one. So in over here, if you just go through this example, so you go through both this blog and example, especially there are multiple models discussed in this, but you need to focus on this one only because you need to choose a particular mode, whether it is higher order mode or fundamental mode. You need to choose that particular mode from a large number of modes that you are searching for. Other all of them are leaky modes or trivial modes. So for example, here I have searched only for 50, but in your case, you might need to search for 200, 300. Now, from that 300 modes, if you click on checking each of them, it might be very difficult to find out which is the mode of interest, right? So here, what I'm doing, I'm integrating the power over that particular mode or that particular core that I'm interested, and see where the power kind of increases significantly as a function of the mode index. Okay, and then I'm seeing that particular area. So just go through this, and if you still it's don't think that it's not helping you, just let me know in the coming days.
Okay, sir.
Hello, sir. Uh, this particular blog will discuss about the propagating mode, right, and the leaky mode. So, can you tell me about how we can calculate the radiation mode or find the radiation mode in the fiber?
How do you define a radiation mode? Means am I missing something? Sorry.
So, like these modes are bound mode that propagate inside the
Okay,
core,
okay.
and few will go in the clad that is called leaky mode,
Okay.
and then there is a radiation mode like we also see in photonic crystal what is light is going above the airline, that is radiation mode. So in fiber also radiation mode I read in few papers. So how can we identify this?
Radiation mode about the airline means I don't
Like in
know.
photonic crystal we can differentiate by making a airline, and up above that
Correct,
modes are
correct,
radiation mode. But in
correct,
fiber
correct.
also, like these modes are propagating. But like when we do experiment, after some distance, these radiation mode will automatically go away.
Correct, correct,
And
correct. Yeah.
also the leaky mode. Leaky mode will go some longer distance.
Correct, correct, correct.
So,
Radiation
like,
mode, I'm not sure how to calculate or how to find it. I'm not sure about that. Radiation mode, but yeah, the one that you said, especially for propagation modes, mode analysis can be figured out. Radiation mode, I think you need to solve the complete 3D model to know how it is going. I don't know. Have you seen some papers talking about
okay,
it in
I
Optical?
will share some reference about that. Particular one old book that is fiber optics. Top some book name is Love and something. I will share that reference actually.
Okay, okay, that's good. Yeah, so I think I have still time to discuss on this higher order modes. So I think you can see my screen. Yeah. So for higher order modes to search, you can just increase the number of modes to 10, for example. Okay, in both the cases, and then you just go and so if you search for 10 modes, and I will recommend then you don't run this frequency domain, because what you want to do right now is only the boundary mode analysis. You want to visualize all the 10 modes. Okay, so you just compute all the 10 modes, and then visualize. You can see all the 10 modes one by one. How does it look like? For example, this is the uh, fundamental mode, and then you can see this is one more type of mode, and then you can keep on seeing. So for example, this is the mode that you are interested in, okay, to propagate along this domain. You can visualize others part as well. Okay, you can see all the different kinds of modes that may be propagating through your geometry. Okay, for example, this is the one that I'm interested. So it actually you need to just copy paste the exact value. So it's 1.1086, right? So you need to just write 1.1086 over here instead of
Sorry.
1.5. Yeah.
Putin, sorry, I'm not getting it. Could you please, because I
Yeah.
disabled the frequency domain, and then we have to click on compute again. Go
Yeah.
to,
Hmm.
yeah. So I clicked on study and go to compute, and after computing, I see that I cannot evaluate expressions. There is a error I am
But
getting.
yeah, okay. Don't worry about the error. Just go to electrical mode field and try to
Yes,
visualize the separate mode fields. Are you able to visualize separate mode fields?
when I am clicking on the next, so it says cannot evaluate expressions. Can I share
Oh,
my screen?
yeah, yeah.
Can you see my screen? So when I click here, next, it gives me an error. Cannot evaluate expressions.
Can you please click on plot? Okay, okay,
Yeah,
okay. But
yeah,
actually,
yeah.
so while sharing, you share your full screen. Otherwise, we are not able to see the error actually.
Yeah,
Can you?
wait a minute. Yeah, wait a minute. I'm
Yeah,
sorry.
you can share your entire screen rather than a particular. I don't know. I'm not able to see that error
Now you can
somehow.
see my complete screen.
Yeah, just hold on. It's maybe loading. Yeah, now I'm able to see. Correct. Yeah. So undefined variable alpha port one annotation undefined. Okay. So go to the line one. What did you put in the line one? Okay. What is in annotation? What is it in annotation? Yeah, just disable this annotation. Just right click on this annotation and disable it. Yeah. Now go to the line one plot. Yeah. Go to the line one plot. Okay. Now go to the electrical field field mode. No, the top one, not this one. electrical mode field port 1. Okay, yeah, there are a lot of things you're doing. Okay, yeah, go to the next now. Instead of either effective mode index 0.89, change it to 1.44, for example. Yeah, plot it. Now you change. Yeah, so yeah, so you can see
Nice,
this
nice.
one, right? So this was what this is the different all the modes that we are working with now. Okay, looks good.
Thanks.
Okay, let me share my screen. Yeah, so now for example I want to launch this particular mode, right? So I know what the value of this mode effective mode index is 1.10862. 1 point, so you just keep it write it on a page of paper and then just paste it over here. 1.10862. Okay, ideally we should write with 16 digits. That's the best way. But this is also should be able to capture. And then I enable my frequency domain. Just in boundary mode analysis, I put these values instead of the 1.5. Okay, and then I launch that particular mode. So it will launch that particular mode only now. Well, ideally, it should launch. Let us see. So here, as you can see, right? So it's launched not the fundamental mode, but that particular mode that we launched. So here you can see, right? It's not the same one. It's not having the power in the center, where it's now divided into two halves. Okay. So based upon your requirement, you can choose the higher order mode that you want to launch. Okay. So you can also export this animation from converting this target from player to file, and then just click on export. Okay, and you can put this into a PowerPoint. Okay, so you can just add to a PowerPoint, and this I'm just showing so that you can actually make some cool animation and show to your colleagues. It will take some time. You can change few of the resolution if it will take more time. Frame per second you can reduce to make it more slow, and a lot of things you can actually change. Mm. Yeah, so it has exported. Now I can use a PowerPoint. Will it open now? Or yeah, meanwhile PowerPoint opens. So any question about higher order modes? I think there are a few question higher order modes. So what were your question? Now you want to calculate the
Uh,
power for the higher order modes, right? So
yes, yes, yes.
you do the same thing. So cut line now in the same area, and then now it uses a lossless domain. So you can make this effective index to be 0, and then again run the model, assuming that it is a lossless. Okay. Yeah. Meanwhile, I'll just show you the results. Hopefully, if it works. Okay. So here you just drag and drop the animation. I don't know. It becomes very slow now in my system because perhaps I'm using COMSOL. Yeah, so you can hear it as animation is dropped, and then just make a full screen and you can see the animation actually working in the PowerPoint. So you can use this kind of cool animation in your PowerPoint to make it more interactive of your work. So even though you're modeling this 2D simulation, you can actually have a 3D simulation results actually out of it, which showcase a lot of things, like for example the higher order modes, the losses because of which it is dying down after some time, and a lot of things. Okay.
Uttam, could
Yeah.
you please repeat this step in console where you enable the frequency domain and put the value?
Yeah, not in the frequency domain. In boundary mode analysis, you need to
Yeah,
put this
yeah, yeah,
value.
yeah, 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 yeah. I know this. I have put this value in the boundary mode analysis and boundary mode analysis one. and in frequency domain, I enable the frequency domain. Then what we have to do?
Then you just need to study it, and then you can see how it is launching.
Yeah, I did
So
it, but yeah, I did not get it.
what is it
So
showing?
yeah, it's showing just the graph. It's showing. It's just showing the graph.
Graph.
I will share my
Yeah,
screen.
yeah. Just
Full.
hold on for 2 minutes. Let me
Sure.
just find this power. I think one more person was talking about the power. So now we have this electrical field. Let's disable the height expression. So let's see if it makes sense or not. Disable. So did I miss something? I put this to be 1 power minus 6. But I'm not getting this mode anymore. Okay, it is okay. I see. So the thing is that your effective refractive index changes based on the material properties. So now, if you're dealing with lossless domain, then you have to again find what is the effective refractive index. Okay. So for example, now I'm saying for the mode field, I need to change. This is the fundamental mode. Okay, here I change, so but that's fine. So for example, which mode I want to propagate for this now? So it's now 1.11634, 1.1111634. Okay, so this is what I'm using, and then I enable my frequency domain, so that particular mode will now propagate. So you change the material properties, you have to also calculate your effective refractive index again. So now you're launching, you should be able to launch that mode. Just let me check once more. Yeah, so this is the mode that you were launching, right? And now for this higher order mode, you want to calculate the power. So you can actually do it over here. So this is for the higher order mode. So it's on 0.038. Very less power in this particular mode. So based upon whatever mode that you want to deal with, you can actually work with.
Now, sir, question is that we are able to get the power for that particular mode. Now, we have several modes. So, what will be the total power? So, how we can calculate?
Yeah.
Like we have to calculate for power per one mode, second, third, then
Correct.
adding that or total
Yeah.
power
No, you
by
have to
some other method.
one by one. We have to launch and see what is the power. So there is no other way. You have to launch this particular mode. What is the power flowing? So this is with this particular mode. So longitudinal. So perhaps I don't know. Don't have time today, but then tomorrow I can talk about a transverse cross section. Right. In the transverse cross section, I can show you how you can doing mode analysis. You can find out the power using mode analysis, and again you need to change. Right now it's a little bit difficult because you're also running frequency domain, but when do you do a transverse cross section, you don't need to do frequency domain because propagation is not required. So with boundary mode analysis itself, mode analysis, you can itself find what is the power. Okay, so it
Okay.
becomes a little bit more simpler. Here also you can do it, but it's little bit more complex because you need to work with variables which are like tangential components and normal components. So this little bit more complex. But most of the times people work with vertical cross section, that is transverse cross section. Okay, so
Okay.
tomorrow I can show you how to do that for higher order modes in a transverse cross section.
Okay. Sir, one last question that Sujay has already asked. This is similar to that. Like at that time, he has asked that why we are launching power only in the core uh,
Okay.
in measurement, but here we are launching core in clad also, right?
Yeah, I mean that
Now
is not in
suppose,
our hand. Means this is the one kind of a mode, so it's not even in my hand. So
okay,
I'm just searching for which what are the different modes that may exist. Okay,
okay. Now
so
my question is that
hmm,
suppose near to this core we have another core, right?
okay,
Now I want to launch power only in one core.
okay,
Then
yeah.
because suppose mode coupling we want to see if we
Yeah,
want
yeah, yeah. So
power.
there is one example. So there used to be, I don't know now it is there or not. So
That
what?
example is there actually.
Yeah. So
I
what
think.
people do is they launch two modes. So and then they superimpose the two modes, and then so how do I explain? So let me just see. I don't know if you're able to explain, understand or not. But what in that example, I don't know. It was the old model.
Actually,
So
I have read that example and
okay.
also the reference paper,
Oh,
but I could not find, means I could not understand, you can say, in that
yeah.
way.
No, so basically, for example, there are two codes. Okay, so
Hmm.
you try to search for multiple modes. Okay, one of the mode would be like both the power it will go. Okay, so I don't know,
Hmm.
maybe this is the way to write it perfectly. Another mode it will give you anti-symmetric. This is symmetric, this is anti-symmetric.
Hmm.
Okay, then what you do is that you launch both the modes together.
Yes, that they are
Okay.
doing. Yes.
Yeah, so same thing what they are doing, and then you are actually getting this mode because power is not important, but this other mode actually gets disabled. Disabled means it gets nullified. So you get power launching. You're launching only with one mode. I don't know if now if there are any better ways to do it, but this is what it used to do earlier.
Mhm.
Yeah.
Actually, the same method they have given in that example, but
Mm.
they have also given some equations in that
Okay,
starting.
okay. That I
But
don't remember
uh,
exactly.
but
But
I
this is
could
the
not.
main crux of what people used to do to if there are multiple modes. Because if there are two things, right? So always you will see both the modes propagating because both of them are having the refractive index. Yeah.
Actually,
So
in
I would
that
like to
example, yeah.
continue,
Sorry.
continue.
So in that example, I just wanted to know what will be the input power for that particular mode.
So
So
here, yeah. So that's what I'm saying the value of power, it's what is input. It's kind of you can make it by default. It is one everywhere. Okay.
yeah,
So
but
instead of
now if two core is near to that, when we
mhm,
launch the power, by default, if there is any coupling from the
okay,
very starting, power will means some power will go in this core and some power will go in that core, right?
okay.
So how we can find
No,
out
that you can,
how much
as
coupling
I said,
is?
you can do a surface integration and then you can find out. So even tomorrow, this is a transverse cross section, right? Even then you can do a surface integration over here and put an integration of power which is flowing inward.
Mhm.
Okay, power outflow. Tomorrow I can show you. So you just do a surface integration over here across this surface and you find what is the power flow.
Okay, means
If
tomorrow
based
we
on,
will
for
discuss.
example, one is radius big, another is smaller radius, right?
Mhm.
So you can see, you can find out the power flow, outflow.
Sir, in case of multimode propagation, can we use this integration technique to find
Yes,
out the
yes.
mode
Modes. Yeah, the same thing as what
power
you
of the
see that
mode?
equation. Yeah, yeah. If you see that equation, it is the integral of the power four, and then I have integrated this. So, for example, this is the power of one first effective refractive index, right? Similar to this, there will be many other. So, if you see that plot that I was showing, so there will be one effective refractive index. Now it is 10. It could be hundreds in your case, right? So when the power flow is very high, so it means that a lot of power is flowing through that particular mode for that particular refractive index, right? So you will see something like this. Sometimes peaks will happen, right? So those peaks are nothing but the fundamental mode and higher order modes.
Okay, sir.
Yeah. So you need to see when the power significantly increases in those particular effective refractive index. So you'll get index that is 1 to 100, not the values. And then you have to correlate from the number over here to these values and then launch that if you want to launch. Yeah. Okay. It is good.
Okay,
Sir,
sir.
I would like to,
Hello.
yeah.
Yes. Yeah, you were saying
So
something?
this is the question. Like, can you show me how you did the presentation? Like how you exported the animation file to the presentation? I just missed that part.
No problem. Just have you able to create animation till now?
Yes, yes.
Yeah, just change the target from file to play. Sorry, player to file, and just click on export.
Okay. Oh, that's it.
Okay, that's it. And then
Okay,
just
thank
drag
you,
and
sir. Thank
drop to that GIF file to your PowerPoint.
you. Okay, thank you. Thank you, sir.
Mhm.
So Sujay here.
Sir,
Okay.
Yeah, Sujay.
Should
Yeah,
I
Sujay,
again?
go ahead.
Yeah. So one thing. So if you go to your drawing, I actually was like for 5-10 minutes not available because I had to attend my kid.
Okay.
The bottom graph that you showed,
Okay.
the effective, you talked about it in this second session.
Yeah, correct,
Okay,
correct.
then
Yeah.
I'll watch the video again and read. Okay,
Yes,
but
yes.
okay, my question is, so if you again, I could be wrong, but if you, so a couple of minutes back we did this experiment where we found the non-fundamental mode, we found the effective index, and we launched that mode particularly. Now, generally, even if we launch one particular mode, it will excite other modes. So when you try to, so even if we tell COMSOL that okay, only launch this mode with this reflective index, but as we propagate through the medium, multiple different modes will be excited. So now when we calculate the power, it won't be actually correct, right? Because the some portion of the power will also be distributed towards the other excited modes. Is it correct to understand?
Yeah, I mean, it's this kind of mode conversions. You're talking about mode
Correct.
conversions that
Correct.
happens. So it mode conversions. Uh, yeah. So
Because when we launch fundamental mode, 10 other, and if we say that find 10 other modes, if we tell
yeah.
COMSOL
So
find
what
1,000,
integrating is the overlap of all the modes that are existing
correct,
through that propagation.
correct.
Correct. Yeah.
So
That you
finding,
cannot. How can you differentiate? Because eventually it's just electrical field at
correct,
each node point. So
correct.
to
So it will,
differentiate between these two, it's very difficult.
correct. So finding one particular mode power would be a little bit tricky,
Yeah.
right? It won't be
Yeah.
that just
Yeah. Correct.
integrating.
Correct. Just
So
hold
yeah,
on. I'm
so
getting an important call. Just hold on. Sorry. Yeah. Sorry.
yeah, may I go ahead? Yeah.
Yeah.
So,
Please.
so the power would be a little bit tricky, but anyway, if you have a solution, it would be good to good to know.
Yeah, I
And
understand. So the way to deal with it, especially for RF microwave problem, RF module, is the way that what they do is that if you are trying to excite from a particular mode, for example, it is TE11 mode in RF waveguide, and port 1 you give as TE11 mode. At port 2 you also have to give it is TE11 mode. So only this mode will exist.
okay,
Okay. So source would be TE11 mode and output would be also TE11 mode. So even though there are any other modes which are being generated, but it would be present, but this port condition will only cater to the this particular um, TE11 mode. So I can have multiple ports here which is another would be like TM10 mode. I can have one more port assigned to the listener port, which is working as TM11 mode. Another port I can assign here. So here source there is only one port, but listener there are multiple ports. So this is how they actually quantify the power flow on higher order modes. So there could be some kind of obstructions, for example. So I'm giving a fundamental mode, but because of the obstructions, I can do the mode conversions to higher order modes, right? So that way is there for RF module, but here we are using port 1 and port 2. So here also it should be possible. So here we need to again apply multiple ports. You understand what I'm saying? Again, multiple ports and then multiple boundary mode analysis. And based upon that particular mode, for higher order modes, you need to put that refractive index.
Okay.
I don't know. You've not listened to that earlier part, so perhaps I don't know it's clear or not.
No.
Yeah.
So this part I understand, but what I mean is, like, for example, even if you do this, if you go back to the boundary mode analysis.
Okay. This one.
No.
Sorry.
Can you in the COMSOL?
Boundary mode analysis. Yeah. Here.
Yeah. Even if so, right now, if you put the search for modes around some value, right?
Yeah.
So that means COMSOL will launch that mode and do the
No, here.
simulation.
So here, it will launch only the fundamental mode. Okay.
The port 1 is okay. Understood.
So but port 2, port 3 are all the listener ports. So I can add as much as number of ports that I want to have. This for higher order 1. For
Understood.
example, this is for fundamental mode.
Yeah.
This for higher order 1. This is higher order 2. So multiple ports I can use for higher order modes to just absorb all these modes. So
So,
ideally, if there is, sorry.
so similarly for cladding portion port 1, core port 2, another cladding port 3. This is the way I have to give.
Sorry, in what context are you talking?
So the multiple higher modes you were talking about, that port
Okay.
1, port 2, port 3.
So here you're giving to the complete exit port, right? So here, so all the three you selecting together, core and cladding. This is core and this is for cladding. So all three you select. So what was the question? Sorry.
Sir, actually, I was saying that if I have multiple modes propagation, the higher order mode propagation, should I have to give port 1 to the upper part of the cladding, port 2 to the middle portion of the core, and port 3 to the lower part of the cladding? Is this the way?
No, not like that. So here, what I'm saying is that, so
you are catching all the power that comes to the output, and then
correct,
you are only
correct.
reading through the different ports only particular mode power.
Correct. So here I'm launching here using the port 1. That is the whole thing. Is from port 1. Okay, and here over here I can apply as many ports I want can apply. I can apply P2, P3 port, P4 port. Okay, and assuming there is some kind of conversion happening over here. So here we launch fundamental mode, but for example P2 is for fundamental mode, P3 could be for higher order mode. Okay, P4 could be for even higher order mode, right? So all of them I can capture using this one. So now if I'm mentioning PS21, it is the power for the fundamental mode. If I'm talking S31, means it is the power flowing for this or higher order mode, assuming you're giving the power input as the fundamental mode. So S41 will tell you about the even second order higher order mode, for example, assuming you're giving a fundamental mode in over here. But that surface integration, if you do that, you cannot do. You have to play around with the port. Surface integration will always have all the electrical field involved in this one. So
Whole
surface
power.
integration so you use this port setting, because port setting has the capability or ability to differentiate the power flow for particular modes. But yeah, this is what is mathematics. This is like principally this is how people do, but you need to sit and check like how it is, how much true it is, this one. But principally this should work.
Hello, sir. This is Krishnan. I have a question.
Sir, may I continue? I have.
Yeah, please, Sujay.
Okay.
Sir,
So
instead of using these multiple ports, is it possible to use the user-defined port here, like where we can try to excite only the higher order modes?
Yeah. So sorry, actually, Sujay had one follow-up question. I will answer this question again. Okay, Sujay, you had some follow-up question.
Yeah.
Please go ahead.
So So thank you for the solution. This makes a lot of sense and it should work. I have two small questions, and one is like, see, if I have the surface roughness values of the side walls, I'm talking about
Okay.
for photonic waveguide, and I will have say either from profiler, wafer profiler, or from AFM surface roughness values. Can I import the values as a sidewall reference and do the simulations that way? Is it like a
Okay.
doable
Okay.
scenario or
Cool. So,
tricky?
yeah, I will answer this surface roughness point. So, because I didn't want to move away from this topic,
Okay,
so I will again
good.
jump to Jai Krishna because he was
No,
talking
no,
about
yeah, we
user
can.
defined. Yeah. So, I just answer his question because it
Sure,
was more
sure,
in context of this. I thought you heard
sure, sure.
about this one. So, Jai Krishnan, so your
Yes, sir.
question was user defined ports.
Yes.
Uh, yeah, user defined ports is not easy to use. So if you are an advanced user, only then I will recommend to use. Okay. So in user defined port, you have to define your own equations of the modes that are going to propagate. So if you can write your equations of the modes, then you are okay. You're good to go.
Okay.
So, but you need to be more mathematically apt to write those equations. Okay. So that's up to you.
Okay,
Means
sir. Okay.
if you are okay to put your hands into those equations, then it's fine. Okay.
Okay.
Coming to
Thank you.
Sujay's question,
Sir, before you answer that, I have a,
yeah,
again, because I wrote that and I forgot to ask. So if you,
yeah,
in COMSOL, if you say that find one mode or find 10 modes, this
okay,
enabling this option, does that,
okay,
I think it does not make any difference in the values. Because if you tell only find one mode, fundamental mode, and you
okay,
find power, and then you say find 10 modes and you find power, because when you're finding 10 modes, some power has to go to the higher order modes, and you will have certain reduction in the fundamental mode. And on the other hand, when you ask it to only find fundamental mode near the refractive index of the core, it will certainly have a different value of the power or the values of field.
yeah.
Will that make a difference, or it will not?
If I understand your question correctly, what you're saying is that if I'm launching this fundamental mode over here,
Correct.
you are saying that at the output, uh, we will only see the fundamental mode over here, not the other modes. You're saying, is
If we
that
if
right?
we tell it to find one mode, then we
But
will in the
yeah, I
result will
understand.
find
Yeah,
one.
no, no,
Yeah,
no. So the catch is that this is the simple geometry. Okay.
correct.
So in this case, might be there is very less chance of conversion of from fundamental mode to
I
higher order mode.
understand.
But there are a lot of other geometries there are significant
Sure.
chances of creating higher order modes. So what people do is that in addition to port 2, they apply PMLs. Okay, so port
Okay.
2, if it is for fundamental mode, is only going to absorb the fundamental mode. The other modes are going to get reflected. Okay, so that's why people use, if there are large chances of mode conversion, so they use in addition to the port also PMLs, because
Mhm.
those PML those higher order modes can actually uh, reflect
Reflect
from
that.
this
Mhm.
boundary and then change the results actually. So if in some of the models you will see that PMLs are also there to terminate the higher order modes. Okay,
Mhm.
so other way to terminate is to apply port for each and every higher order mode. So you can use 10 modes, for example, for each and every other higher order modes. In that way, you don't need to apply PMLs. PMLs is a versatile absorbing media, so it can absorb whatever is given to it.
Mhm. Yeah, I always find this PML as a little bit cheating, because you in real
Yeah,
life
yeah.
you can't have this kind of material
Correct,
which
correct, correct.
absorbs
Yeah, I
everything, and
understand. Yeah,
it's like
correct. Yeah.
best thing to have in your life, but that doesn't
Yeah.
happen. Okay, yeah.
Yes, that's true.
Yeah, but so this roughness and bend part, because
Huh.
I have some results from AFM which I
Hmm.
could then
So
feed into
where
this
is the roughness that you're talking about?
the sidewall roughness of the waveguide.
Which side wall over here?
No, no. So you see the core region. So
Core and
consider
cladding
this is a
interface?
consider, yes, correct. Consider you have a slab waveguide, 220 nanometer by 500 nanometer, typical silicon photonic
Mm-hmm.
waveguide, and
Mm-hmm.
the sidewall roughness could be given by profilometer or AFM. And then I want to just do, because one other way of doing is like you do Monte Carlo simulation and try to do mathematical um, permutation combination to find out what is the best and worst case scenario of your
Mm-hmm.
fabrication method. And the other way of looking at it is like, if you already know how your fabrication is behaving, you already know how your structure looks like, and for that particular roughness, how would your structure behave? So something
Yeah.
like that. That would save a little bit time in like overall fabrication
Yeah,
process.
yeah, yeah, that is true. So there used to be this transition boundary condition usually to be applied to this some kind of yeah, I don't know. But actually one way to do it would be to do geometry wise, means you have that geometry input with those roughness, but that doesn't make sense because it will make the model very computationally expensive.
Mm.
To apply surface roughness, there is with RF module with the transition boundary. So let me just add that. There is some. Let me just add physics EMW interface. So it's in part of radio frequency EMW. In this EMW, there is transition boundary condition. Oh, I think it's over here. No, here. Yeah, surface roughness. You see.
Uh-huh.
So here means if you, but you have to use EMW interface, not EWFD. So somehow they have not used this in. So here you see roughness, surface roughness, and you can mention what kind of roughness, the mean surface roughness you can add,
Correct. Correct.
and then which kind of surface roughness is snowball, or
Correct.
you could have a, sawtooth, and then is
Mm.
it physics control, skin depth, or user defined. This was especially for metallic materials, but this transition boundary condition could also be used for dielectric material, so that's not a
Mm.
problem. But this specifically for thin boundaries. I'm just thinking how you can
Because
correlate
skin depth won't, yeah. So that is like application is different, nah? Because
different.
you are
Yeah,
not
yeah,
flowing
correct. Yeah,
electrons, you are flowing
correct, correct.
photons through it. But yeah, maybe I can
Yeah,
look into it. I
yeah,
was not
but yeah,
aware.
this is a good point. Actually, you can even write to the support to add this kind of
That
like
would be
what
great.
you can
Great.
do. Yeah, yeah. This is, but yeah.
Yeah, like, I'm actually quite new to COMSOL. I was not aware.
Okay, okay.
And someone
I don't
new.
know, with some kind of random roughness also can be add over here. So some kind of randomness is function is over here, right? So
Mm.
if we use that randomness and create this line with that surface random roughness with a mean value that you mentioned.
Yeah,
So
that
with that, if you can do, then it is something which is. But
that would
the
make a lot
problem
of
is that your mesh should be able to resolve that roughness.
yeah,
Else, what you
definitely.
become life will become hell.
No, but then I do the simulation on my server, which has like ton of
Yeah, yeah,
value.
yeah, yeah. But
That
that's
would,
how you have to do, because otherwise it will be very difficult. The roughness
yeah,
itself would be in order of nanometers, I guess, right?
yeah, it is
So
right now 30, 40 nanometers.
yeah, so
At
you have to
best.
resolve those roughness
Correct,
using the
correct,
mesh. So you
correct.
can use that special. You can move from physics control mesh to user control mesh, and then you can apply this size node or a specific size to this particular boundary instead of this entire geometry to this boundary, and this you can make a little bit up, and you can make a very extremely finer mesh. So you can have, so you can go even custom and make it even more. So whatever is the thickness of that guy,
Mm,
30 nanometer, right? So that you can make, and it will actually make it more refined over here.
mm,
So on that edge you can actually go on it and decrease, so it actually will make it, you should be able to refine. So now it is with 20 mm, so you can see it's
mm,
propagating, so it
mm.
should not be a big problem unless until you're working with 2D. 3D would be very difficult. Yeah,
Yeah, at least to get some like ballpark value, right?
yeah,
So
yeah,
at
yeah,
least to
yeah.
something to
But
start
yeah,
with,
I
and
think
then
with
it
you
will
have to
be.
work with geometry, so you can change this geometry of this if you have the geometry with you, or you can use random function to create a
Mm,
line with having this mean value of randomness, right?
mm.
So with that you should be able to get it.
So the goal is actually to have a 3D very small, so 50 micrometer by
Okay.
100 micrometer length, 50 micrometer core radius waveguide and do some crazy 3D simulations, but that would take a lot of time. So just I'm
How
trying to
long are you
see.
talking about? How long
So
length?
length doesn't, yeah, 100 micrometer would be more than
Micrometer,
enough.
100
Yeah.
So we have this example. I don't know. Have you seen that or not? Actually, we published this over here. So this is this we have done with this. There is specific beam envelope method if you're interested. So here, especially, you can see this is the for 2D, but we also were able to do it with 3D. So this with the three. This is are almost like how much? Uh, Almost in order of micrometers, I guess. Yeah,
Mhm.
around 10 micrometers. So the
Mhm.
huge long 10 micrometer deep waveguide. Okay,
Mhm.
a slot waveguide. I guess this is for the deep waveguide. I guess. Yeah, silicon
I'll take a
waveguide.
look. Mhm.
Yeah. So it's how actually propagating. Yeah. So this is also you can use the bound beam envelope method, and using the same boundary mode analysis, you can actually do this. I will share with you if you're interested. You can
Sure.
go through these example models. Maybe
Sure.
helpful. Okay.
And maybe a last, we already discussed about this. So if you can find some information on source location and then playing with the different location of source, that would also be something.
Yeah. Correct. I remember. Yeah. If I find out something interesting, I will definitely get back to you on this. Yeah.
Yeah. Because it is a long-standing thing, and I am not sure whether it is possible or not. If it is possible,
Correct.
then
Correct. Yeah.
I'll do it.
Yeah. That's
Let's try.
very. I don't know. I mean,
Peculiar.
there's some workaround is possible somehow, but we have to think a little bit longer. Yeah,
Sure.
but some kind of workaround should be possible. Means there's some kind of mismatch of the material. You can make it a little bit up and then down and
Mm.
then that kind of thing. So you can actually what I'm saying is that you can so instead of rectangle over here, so what I can do can I extrude? No, I cannot extrude. What I can do is that I will duplicate this guy, and make this weight to be around zero point 0.1, make this to be around zero point 0.1, pull it lower. Yeah, something over here, and then I can actually move it little bit above. I don't know how it will work, but just trying to see if it will work. Very minor modification, not much. So I'm moving it a little bit above. Okay,
Mm.
and then try to see how it works. I don't know. So you can apply this core and cladding thing.
So you have added a small section before,
Yeah, correct. So and then I'm trying to launch with this.
but then I'm worried about the first boundary that it sees on the
Correct,
longitudinal side.
correct.
So that
That's
could
a, that
actually.
is, yeah. I don't
But
know
yeah,
how
it
much.
is good, good.
So
But
it's
yeah,
kind of.
I will have a
How
look
come
at
this
it.
becomes the same thing? Almost the same, right? I don't know how come. Should be a little bit shifted up, right?
Should be shifted.
Maybe the same guy.
Huh.
Okay, here I can just make this guy a little bit upward as well, or downward, doesn't matter. So four,
You have point four, point four, point four.
yeah. Then I don't need to use this move, and then I can launch using this guy. So again, this point 4 is still very high. 0.545. I don't know. I'm just try to see if doesn't make sense or not. Even. I'm trying to launch the fundamental mode and see because of this how much is going to propagate. Okay, transition. I forgot to delete this guy. Yeah, I don't know. You have to back it up with some experimental results. I don't know.
Correct.
So here
Yeah.
I'm just launching a little bit above. So you can see, means I don't know, little bit changes there as compared to before. But yeah,
But
maybe
definitely it is. Yeah, yes, you can
some
see
launching
the.
little bit above as what it should be there. So
Mm,
yeah, that's how it's okay. Looks good. So you can play around with this, for example,
sure.
like this, and you can see, for example, if I move a little bit even higher, okay.
Mm,
Someone still wants to join. Okay.
maybe by mistake they left.
Yeah. Now
Okay.
it has to become crazy.
Okay. 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 But yeah, let me play with it and see
Yeah,
where
I
it
think you can
lands.
see how it makes sense. But if you do too much, then it's what it become crazy
Yeah.
actually.
And anyway, this is just a mathematics. I don't
Yeah.
in substrate how it behaves is.
Yeah. One other way is to use some kind of PCs around this one to work with. So that also is there. So because PEC is nothing but perfect electric conductor. So over here you can actually apply, for example, here you can apply this PEC to this. You can apply only kind of PEC apply over here and here. So then it, but mismatch is that it's just moving up and down, right? So
Hmm.
yeah. Or
Like for example,
otherwise,
in the experimental part, if you have a, let's say, fiber prober
mhm.
on your chip, and then you do this manual alignment, and then you do this piezo alignment.
I think
Um,
one way is to do another. Sorry, I just interrupted. One is the
yeah.
way is to use using the lens, focusing lens. That is the best way to do it. So there's example
Uh-huh.
on focusing lens. So I think that is over here. That is a very good example on focusing lens. And so you need to put this focusing lens in front of it, with the light source, and then you can work around. So here you can see, right? So it's millimeter level focusing lens. So you try to focus it around this, so how you give it inside. So I think that should be able to do it. So it will be more. So this is a focusing lens model. So
Mm-hmm.
with that you can try to focus this. So
Okay.
yeah. So this is how it actually focuses. So this is the lens over here. It's a plano convex lens. You try to focus it over here. So maybe you can play around with the lens system. I think that
That
would be the most ideal way to
correct. I
focus
thought
this.
lenses are
Right.
only
So
available in the ray optics module.
no,
Here
no. This
also,
is a
I
very
don't know.
small lens. You can see it's just 0.2 lens.
Yeah. Yeah.
Yeah. So I think with optical fibers, which are itself in dimension of micrometers, I think you can still work around with this one. Should
Mm-hmm.
not be a problem. Yeah. So, yeah.
Yeah. Lens is
Micrometer.
yeah.
Yeah. If you're in micrometer orders, then it's fine. Yeah,
Mm.
lens. But you have to go to in order of then it's very difficult.
Yeah, yeah, that's right. And it will
Yeah.
take a huge amount of
Yes, yes, yes.
processing power.
Correct. Yes.
Yeah, perfect.
Looks
Thank you
good.
very much, sir. Yeah.
Yes. Yeah, looks good. So let us meet again tomorrow at the same time and take this session forward. Okay. Tomorrow we'll try to see we can cover this optical fiber, and then we can go ahead. So Abrar, do you have a question? You have been raising your hands.
Sir, can you discuss the grating inside the core if possible?
Greeting inside the core. Yeah, in one-on-one session we can definitely discuss because we have
Because
to
I
cover
want to
not only.
design an FPG in the optical fiber and I'm not
Yeah, yeah.
understanding how should I
Grating.
proceed.
If there is an example of of this grading example is there, so we can discuss. Should not be a problem.
Or
Okay.
particularly FPG in the case of optical fiber.
Yeah, means we can discuss in one-on-one session. Means
Okay, sir.
because we have to cover the schedule. So yeah,
Okay,
yeah.
sir.
Abrar, you have a question? You, I don't know. You can unmute yourself and ask. Okay. Or Ayushi, you have a question?
Hi, sir. Yeah. Sir, can we also discuss in one of the sessions about metamaterial based terahertz filter? I'm actually
Okay.
working on that, and like
Yeah.
I want to understand like how the
Yeah,
physics
definitely.
works. And
Mhm.
yeah, sure.
Yeah.
Thank you very
Yeah.
much.
Looks good.
Thanks.
Okay, looks good.
So
So
I have a question, just one question.
okay.
Uh, so actually, you have told that by launching the higher order mode to the input of the at a port one. So how we can import, like by putting the reflective index as for modes around here, or
Sorry, can you come again?
actually you are telling that higher order mode can be launched at the port one.
Okay.
So how can we import, like by putting the reflective index here, the search for modes around here,
Yes,
or
yes. Yeah, effective index, you need to put the values of whatever is the effective index um
Mhm.
of the that particular mode.
Yeah. Okay,
Yeah, you
okay,
can see
that.
the recording. That's what I've done.
Mhm.
I've used that. I've caught off the higher order mode. What is the effective refractive index of that higher order mode and effective? Okay, and then I place it inside this
Yeah, yeah,
bio
that.
boundary mode analysis.
Okay, okay.
Okay,
Thank you. Mhm.
that's good. Yeah, if you still see the video and still if you have doubt, you just catch me tomorrow. Okay, looks good.
Okay.
Thank you for today's session. Let us meet again tomorrow and take it this forward. Thank you. Bye bye.
Yeah, thank you, sir.
Thanks.
Thank you.